Welcome to RPKI tutorial. So this will be in two parts. We'll run a theory session today and we'll do some labs same time tomorrow. So you'll be able to apply what you've learned here. As I said a second ago, I've had a quick look through the list of people that are here already, and some of you I've seen before, some of you I haven't. So good to see some of you again, and welcome to those who are new. So let me get this underway. So I've posted a link over into chat for our training wiki. We have available there our slide deck as well as our lab exercises that we'll be doing tomorrow. There is also a link to the questions document just there, and that will open up over here. In here is all sorts of useful bits and pieces and information to do with RPKI, various links, etc. We also will be doing lab assignments from here. And if you have questions you want to ask that you want to remain anonymous for, or for whatever reason, just throw them up into that doc. So that's linked back from our wiki page. So I'll just quickly throw that into chat as well. You'll need that later on. I hate that. Let's try this again. Right click, copy link address. There we go. Today and tomorrow, Divya will be assisting me, so he'll be grabbing those questions out of Q&A, as I can't see everything on one screen, unfortunately. So if you do have any questions at all that are relevant to what I'm discussing and you want an answer at that point in time, make sure you raise your hand, so that way we can grab that question, as we're talking about things. I want to keep this as interactive as I can in webinar mode. Close that door. So some of these slides that we're using today have been stolen from Jeff Houston and Randy Bush, and there's possibly some others that have been added since. So let's look at some incidents that have been happening over the last few years. So we'll start with, I guess, the most recent one for us, which was the AS1221 Telstra hijack leak on the 30th of September. So around 2 in the morning our time, people started posting in various NOG mailing lists that there was quite a few prefixes that were hijacked. But our good friends at Telstra, they do route origin validation. So how did this happen? As it looks, based on the info that I have from people that I've spoken to at Telstra, as well as their public information releases, they were testing a provisioning script that provisions services, and it went and originated a load of originated a load of prefixes that it wasn't supposed to. So theoretically, that should have been stopped by their Upstream 4637, but 4637 doesn't do ROV yet. Even though Telstra do route origin validation, because they were originating the routes, they became valid. So we'll talk more about that as we move along. So that's probably the most recent one. It caused a lot of pain for about 3 to 4 hours. And I think a lot of people were left with red faces after that one. 30th of July, another hijack. This one from Tulix. But the way these actually propagated and the way it looked, it was very much a case of a Bgp Optimizer. So Tulix were actually originating more specifics of prefixes, trying to do some traffic engineering, and it caused also another lot of pain. The downside with this is 1299, their Upstream accepted those announcements and then went and re-advertised them again. So it just amplified it and made it even worse. This one, 1st of April, it wasn't a joke. Rostelecom in Russia, it went and did exactly the same thing. It went and leaked a lot of more specifics for the likes of Facebook, Cloudflare, AWS, etc. They leaked about 200 ASNs worth of stuff. And some of these peers actually accepted and propagated again. And these aren't little guys. I mean, Cogent, level 3, they accepted these announcements and they went and announced them as well. So they went and repropagated it. So we see the same thing. June 2019, yet another Bgp Optimizer. So anybody out there using Noction, etc., maybe you should really think about it. This one was a bit different, but poor old AS1335. Let's have a look at this in a bit more detail. So AS1335, they went and announced a /20. Level 3 then re-announced that /20, and that went to DQE, who are a manufacturing company. They had a route optimizer, and what it did is it split that up into 2 /21s. They then went and passed it on to ATI, who then went and passed it on to Verizon, who then went and put it out to the internet. So now all of a sudden, those more specifics that were being leaked by DQE were being seen as the more preferred path. So this one here, it was a route optimizer. We're presuming, and this is what Yob said at the time, I strongly recommend to turn off those BGP optimizers, glue up the ports, shut them, burn the hardware, and salt the ground on which the BGP optimizer salespeople walked. Not a fan of BGP optimizers. So Google, they did the same thing. Well, Google went and leaked some prefixes. Traffic was all dropped at China Telecom. How did this one happen? AS3782, main one, they leaked into China Telecom, who then leaked it out to others. And again, it propagated. Basically, they're saying it was a BGP filter misconfiguration. It keeps going. This one was a bit more nefarious. So this one, there was a Route 53 hijack. So this particular one, they were only looking for DNS queries. And why were they doing that? They were trying to get credentials for a crypto coin, my Ether wallet. So what were happening here was anybody that was trying to reach Route 53, the attackers' DNSs would respond, and they were only looking for the my Ether wallet DNS requests. They were then redirecting that to a server which they owned. And what happens then is those users would go and put in their credentials, and all of a sudden the attackers have a load of my Ether wallet credentials. So that one was a very targeted attack and looking at a very specific set of data that they want. Google brought down the internet in Japan in 2017. So they'd leaked 130,000 prefixes to Verizon, normally about 50, and 25,000 of those belonged to NTT. And they put out more specifics, which then was passed on to KDDI and IIJ, and everybody accepted those. So what happened then was we had routes that were taking a very, very long path around the world. This one, I think, these came from Maz actually. So YouTube, this one was a good one. PTCL announced a /24. Basically, they were asked to block access to YouTube. So the engineer in charge didn't realize that YouTube was actually using a /22. He went and nulled, or went and put the /24 in as a null, but announced it back out to his upstreams, and PCCW, they went and propagated that. So that /24 was seen as more specific again, and traffic was sent to PTCL for that. So why do these things keep happening? So there's two main reasons. There is no single authority model for the internet. There is no regulator. There is nobody that says you can and you can't and you will not. And there's no reference point for what's right in routing. So what do we mean by that? Everything is written as a best current practice. Everything is written as a standard. But if people don't actually follow those rules and follow those recommendations, then we see things like, the things we've just seen. And this happens daily. These are just the big ones. Routing also works by rumor. So you tell what you know to your neighbors and you learn what your neighbors know. You know that if you go and say to your neighbor, hey, I'm AS4608 and these are my prefixes, and your neighbor goes, hello, AS4608, no problem. Any traffic for your network, I'll send to you. And we also assume that everybody is being correct. There's no real security in BGP at that point to say you are legitimate owner. So we believe that what you're telling me is the truth. Routing is also variable. So my view of the network here in Brisbane, Australia, is going to be very different from a view in Nepal. And as a result of that, because we've got different routing origins and things like Anycast, etc., where my traffic goes is going to be, and how I get from point A to point B is very different to how you are going to get to it. And there's no one reference view because everything's variable. We all have, or most of us have, multiple uplinks. We have different paths. We may do different traffic engineering. So things that we do my view is going to be very different to your view. And routing works in reverse. So my outbound advertisements affect my inbound traffic, and my accepted announcements are going to influence how I send traffic. So everything works back to front. Steve Bellivan's April 1 RFC. There is no E-bit, no evil bit. Go and have a look at that RFC. But basically what Steve Bellivan is saying in that is, if only the bad guys could go and set this bit to say, hey, I'm doing a bad thing, just ignore this traffic if you don't want it, right? It'd be great if we could all do that, but it doesn't work that way. So a bad routing update doesn't identify itself as bad. All we can do is identify what is good. But the question is, how do we do that? And why should we worry? Because it's so easy to do bad things. It is so easy to make mistakes, tired engineer, mistypes a prefix filter, there might be another disaster with a network, and in trying to fix that one thing, you then go and create another problem. It happens all the time. So how do we stop these things from happening? We've got to start at the top, right? We've got to work with the basics. Filter, filter, and filter. It's all about routing hygiene. So always filter your peers, your upstreams, and your customers. These are including and not limited to prefix filters and prefix limits, AS path filters, AS path limits. I mean, if we look at Philip's example from his routing update, we've got somebody out there that's pre-pending 200 times. Why? Do you really need that much junk? And that's just cluttering up your route tables. And RSC 8212, BGP default reject. Problem with RSC 8212 is not everybody is doing that. So as it currently stands, what are we doing to try and validate that what we're getting from our peers and from our customers is actually correct? So if we look at what we do at the moment, you will get a peering or a transit request from your customer. You'll then go and do a LOA check. So verify that what they have is, and what they're going to advertise actually belongs to them and they're allowed to. And then you set your filters up. So how do we do our LOA checks? We've got a couple of options. We can do a who is. So you manually go and look up and find out what this ASN is, it has assigned to them in resources. You could also ask for a letter of authority, or you can use RPSL. So we do a who is, we're just verifying the holder of the resources. So we have this one here, which is our APNIC training. Go there, sorry, turn my pen back on. So we have our APNIC training prefix here. And you can see that that is owned by me or by APNIC training, and that is our ASN. So you can actually look this up, just do a who is, and always check against an authoritative IRR. RADB, etc., are all full of junk, and try wherever possible to go to the source of truth. You could also ask for a letter of authority. Haven't seen this too many times, to be honest, but basically we can issue a letter of authority, and that is mainly to absolve someone of liability in case they go and do something wrong. The other way of doing it is we go into the IRRs. So what we're doing here is we're validating that you actually have got route objects with your origin AS to verify that that is your prefix and this is the AS you want to originate from. I had a call from a telco earlier this week. One of their customers who had migrated from another Upstream. Basically, the resource holder did not have any route objects at all. So they were using RADB, and that record had been set up by the previous Upstream. So the new Upstream had no way of actually changing that. So they reached out to me to try and reach out to the end customer and get that sorted out. But a lot of your upstreams will be doing a lot of this stuff in some sort of automated fashion. I know Vocus here in Australia, they have a system called CAT. You go and put your prefixes in your ASN, it runs away, checks to make sure that you've got route objects. If it's got route objects, then it goes and updates its filters. So it's another way of doing it. So we can use this IRR data to actually generate our filters for us using various RPSL tools. So this particular one here, we're using Bgp Q3. The nice thing about Bgp Q3 is it can generate filters for you in various formats. So you can either use Cisco, Juniper, or you can even specify custom filter types. So if you're using something like MikroTik, you can actually put in I used to have one for MikroTik, a template, so that you could actually output filters, appropriate filters for you in MikroTik's CLI. So we've got a couple here. The first one over here is looks like a Juniper bird syntax. So that's for AS17660. And we've got our IPs there and our V6 as well. This one over here is also for bird, and yep, and we're using the source. So we're actually specifying that we want to use APNIC for that. Now let's have a look at the differences here. By default, this uses RADB. When you're specifying the source, look at the quantity of routes that we've got that are different. As I said a second ago, RADB is full of junk. Anybody can basically go in there and say, I'm going to be a maintainer for this object in RADB, and this is what I say. And if you're not referencing an actual valid source, then this is what you're going to get. So Tashi has actually admitted responsibility probably for setting this up way back when, and it's still there, I believe. You've got other options with Bgp Q3 as well. So this one here is just what's this one? This is an AS path filter for BT. And this guy here is for one of our bigger ones. So this is building a AS path access list for Superloop. So we're just specifying that the AS is 38195 and we're calling it Superloop in, and it's generating Cisco output. And I can see my old ASN sitting in there. So these are automated ways in which you can go and build prefix lists for your customers. But there are problems. As I alluded to, There is no single authority model. How do I know if a RR entry is genuine? You have to check with the authoritative source. How do I differentiate between current and lapsed? There are loads. I think there's like 27 RRs. There's also incomplete data. As I mentioned before, customer with no route objects. And scaling. So how do I apply IR filters to upstream? So somebody who's giving me a full BGP feed. I mean, this morning the V4 table is 854,000 and the V6 is 106,000. I can't go and build filters for all of that. That's just nuts. So you could try and automate it, but the filters are only as good as the data you're getting. Good old garbage in, garbage out. So as I said, make sure you specify that source. Two options. If you're going to use RT config, then that's a small s. What about this option? Could we use a digital signature to convey the authority to use it? So using a private key to sign the authority, the public key to validate it. Do I need to do a quick primer on asymmetric encryption? Are we all comfortable with understanding public and private key pairs? I know some of you have because you've been in my classes before. I'll do a very, 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 very quick version. Two types of encryption. Let me just throw up a regular whiteboard. Bear with me one sec. Why are you not giving me a whiteboard? Control W? No, Shift W. There we go. Right. Symmetric key. Let's talk about that really quickly. Symmetric key is exactly as it says. We have a key and we have another key, and they are both the same. With this same key pair, if I have some plain text over here and I then encrypt it with my key, I wind up with ciphertext. I can then send that to somebody. They already have my key or a key, and then I can turn that ciphertext back into plain text. Pretty simple, right? That creates other problems because you've got lots of other keys running around. You've got security of those keys. You then have to hand out that key to people that you don't know what they're going to do with it. So how do you get around that? We use, come on, get back. Why is that gone over there? When technology fails. There we go. There we go. I think I'm having Philip's problem from the other day with PowerPoint not keeping up with things. So let's talk about asymmetric keys. With asymmetric keys, you have two keys. You have the public key, and we have the private key. As the names indicate, public key is exactly that. You can share that with anybody. Private key, you keep that and you keep it safe. Why do we say that? Because if somebody has your private key, they can sign, they can encrypt things with your private key. So the things we can do is we can use, I'm getting myself tangled up around my cable. There we go. We can use the private key in our particular instance to sign our resources. Anybody with my public key can then go and validate my signature. They can say, unequivocally that this is mine. I can prove that that's yours because I have your public key, and I can use your public key to decrypt what you have done here. So public key cryptography relies on what we call a chain of trust, right? So if we look at how things are delegated from top down, we have IANA at the top, who gives resources to the RIRs. We then go and delegate resources to the NIRs and LIRs, and then either them or the RIRs will give resources to the end holders. So then we have our certifying authority. So let's look at this. At the top of our chain of trust, we have our RIRs. All these guys. We are the trust anchor for these CAs. Within our certificate chain, we have our NIRs, who are an intermediate certificate. And then they can then sign these resources or the end entity certificates for their resources. So by looking at that certificate, you can establish the chain of trust all the way up to the top. Same down here. If it's a APNIC delegated resource, we are the trust anchor for this, and we sign those resources. You can validate that certificate all the way up. So an RIR holds itself signed root cert. We sign the resource certificates. Any attestation, so anything that is signed by the end holder's private key can be validated all the way up the chain of trust. So that's how our trust works. But how do we do that? So within the PKI structures, RFC 3799, that allows us to bind a list of resources. So those V4 and those V6 resources and the ASN. We also have the subject information access, so that contains the URI that identifies the publication point of the objects. So we're making sure that where things are coming from are also valid. So in reality, how does it actually work? So when an address holder, the RIR, NIR, we go and allocate the resources to the end holder. We issue the resource certificate that then binds those addresses and those ASNs with the EE's public key, and we sign that with our private key. So what we're doing then is we can then use the public key to verify that that is actually correct. So the resource certificate proves that the holder of the private key is the legitimate holder. So now party B can sign authorities using its private key, which can be validated against the trust anchor. Don't know why those dotted lines are there. For routing, the address holder can authorize a network, an ASN, to originate the route and sign this permission with our private key. So that is what is a ROA, Route Origin Authorization. So I don't necessarily have to originate that network, but I can assign the rights to originate that network to somebody else. Same as if you're doing a route object for something that you don't originate. You might be AS1234, but you're not running a BGP session with AS1111. You can say in that route object, origin AS is going to be quad 1. So a ROA is a digitally signed object. So it's going to bind those prefix lists and the nominated ASN, and we can verify it cryptographically. So we're using those signatures, those certificates, to verify that. And you can have multiple rowers for the same prefix. So if you have got some weird setup where you've got a third party originating your prefixes and you're originating them, that's fine. You can have both. Any questions so far about this? Am I moving too quickly for you? If so, please tell me. I don't know if you don't tell me. I'm trying to raise, there we go. I'll get rid of the dots. Nothing there? No, good.
No questions so far.
Excellent, thanks. So what can RPKI do? We can authoritatively prove who is the legitimate owner of the address. We know which ASN has permission to actually originate that address. So what can that help us with? It helps us with things like route hijacks, somebody else originating your prefixes, misorigination, and misconfiguration. So it solves a couple of those problems that we talked about, we saw examples of earlier. We know that mistakes happen. Not everybody's running good filters. So we need to remove the onus or our expectation, I guess, that somebody else is going to keep it clean for me, because that doesn't happen. So let's look at the components we have within RPKI. So we have the issuing party, so that's the registries. So it's the RIRs and the NIRs, so the likes of NREN. We have certificate authority that issues resource certificates and publishes the rowers. So this is the My APNIC GUI. Off to the side of that, we have our own RPKI engine, and we have the publication of those records. So we have the repository. We have the relying party, RPKI validators that gather data from rowers from the repositories and then validates each entry signature to build a validated cache. So typical protocol that we use for doing that is rsync. There is also RRDP, which is preferred, but not everybody's doing RRDP yet. So your validator will then go and pull down those records from the various repositories. And we'll be doing this in our lab tomorrow. So we have a couple of models. You can either do the hosted model, which is the most simple. So the RIR will run the CA. So we run the certification. We manage all the keys, the repositories, and we generate the certificates. But if you've got a lot of address space, you may decide that you want to do your own. So we also have the delegated model. So the regional registries will run their own. So JPNIC, TWNIC, CNNIC, which is an interesting one. I don't know if IDNIC's finished theirs yet. So these guys run their own. So we delegate the CA from top down to them. So they run their own RPKI. So let's look at this. This is a V6 route. 17821 is originating 2406, 6400, //48. It's announcing to 65550. 65551 is connected to 65550. So I'm sitting over here and my AS path looks something like this. I'm getting to this via 6551, 6550 through to 17821. That's all great. How does BGP work? All of a sudden we have 6552 announcing my prefix. He announces it to 6553, who then announces it back to me. Which of these two is going to wind up in my route table? this guy down here. Question is why? Why is that going to wind up in my route table? 1, 2. With no other mechanisms, what does BGP do? Lower AS path, correct. Shortest AS path wins. So guess what? Traffic that I thought was going here is going here. Not so great. So how does it actually work then with route origin validation? Same scenario. We've got the bad guy down here at 65552. We have our global RPKI repositories, so all of our RIRs, and we have a validator. Our validator will, via either rsync or RDP, grab the rower manifest, and it says, oh, look at this. I have a rower for this prefix, 2406-6400, /32 through to /48. And that's allowed to be originated by 17821. On my router, I have an RTR session, RPKI to router session. When that incoming route hits my router, it checks against my validator. And depending on how I've actually set my router up, I can do a number of things. My router will determine that this guy is valid because originating AS is correct and my prefix length is correct, and it will install that route into my route table. The invalid route, that's up to you. We'll talk more about that. So the router goes and fetches the rower information from the validated RPKI cache. All of the crypto is stripped by the validator, and BGP checks each update against the rower information and then labels them. So we've got this concept of labels. I think we touched on this, I think Zabir might have touched on this when he did his manners presentation. We have 3 states. We have valid. So valid is where our prefix and the prefix length and the AS are in the database. Invalid is where the prefix is found, but the origin doesn't match, or the prefix length is longer than the maximum length. We'll touch on that in a second. And we also have not found or unknown, where there is no rower found, neither valid nor invalid. So maybe it hasn't been created yet. So let's look at this one here. Aside from the fact this is RFC 1918 space, let me quickly just flick. So I'm going to be over the board for a bit. There we go. So we have a rower for ASN 65420. We have a prefix of 10.0.0.0/16 to a maximum length of 18. So what we're saying is that any prefixes that are in 10.0.0.0/16, 17, the 2 17s and the 4 18s are all covered by this rower. Okay. So let's have a look. Valid or invalid? 65420, 10.0.0.0/16. Would that be valid, invalid, or unknown? Valid, valid, valid. Correct. That would be valid. We have a matching prefix. We have a matching ASN. Check, check. Beautiful. What about this one? 10.0.128.0/17 from ASN 65420. Valid, invalid, or unknown? Naveen, correct, valid. 128.0/17 is part of this 16 and it meets our max length. So we got a Tick on that one and that one. Beautiful. Valid. What about this one? ASN 65421 10000/16. Valid, invalid, or unknown? Invalid, correct. Why is it invalid? Why is this one invalid? AS not match. Very good. Big no. This one, 65420 10.0.10.0/24. Valid, invalid, unknown. Which is it? Yep, Jitendra, not quite. Yes, the ASN matches, but invalid greater than max length. We said our maximum length is 18. We're putting /24. So that would be an invalid max length. And the last one, 65430 10.0.0.0/8. Valid, invalid, unknown. Oh, lots of invalids. Yahya Khan, very good. Who else got it? Someone else back here. Can't scroll back. But no, it is not invalid. Why is it not invalid? Our rower covers our ASN, our prefix /16 to /18. This is coming from a different ASN, and our prefix is shorter. It's /8. Therefore, it's not found. There is no rower covering this. Hopefully, from a routing perspective, the traffic could still get to you because you've got a more specific prefix. So we now know we've got these three states. We've got an idea on how we actually work out what is valid and what is invalid. And what are we actually going to do with this information? A couple of options. Drop my microphone. Couple of options. You can tag them. So if you have downstream customers or you run a route or IXP, you could just tag the traffic. Or you could modify prefs. Higher pref on valid, regular local pref for not found, and a lower local pref for invalid. Or you could just drop invalids. This one I would be very cautious on initially when you're rolling out. It's always a good idea to watch, monitor, and see what's going on before you go and start messing with customers' traffic. The reason we say in an IXP scenario is you will want your IXP customers, or sorry, your IXP members may want to do their own validation. So you could do that via a community tag or however you want to do that. I always say that modifying your local preference as a starting point is a good idea. Once you've profiled the traffic, made sure that your customers aren't trying to get to these invalid sites and they may be business critical, but somebody at the other end of the world's done something wrong. You don't want to upset your customers. You also have to think about your downstream customers. So if you're filtering your prefixes coming from your customers, there may well be a valid reason that they're sending an invalid. I don't know. I've seen it. Doesn't make any sense. Don't know why people can't clean their routing up. But again, it's all about making sure you're not making your customers annoyed. Annoyed customers make for unhappy engineers. So are rowers enough? What if I forge the origin AS and the path? Yes, it would be accepted as good and would pass origin validation. which then means we need to do something about securing the AS path. So we need to do some sort of AS path validation per prefix. We can use RPKI certificates for this. This concept of AS keys per router. So my APNIC training down here, I have a cert. I have a chain of keys. So I have my CA saying, this is me. I have my entity, which is my prefix, and I have my rower. We also have an AS cert. So that's my AS, and we're encoding the ASN and our router ID. So this is still in draft, but it's a nice concept. So we could use RPKI to validate that the originating router, based on its router ID, is actually allowed to send that. We also have Bgp Sec, RFC 8205. There's a couple of issues with using Bgp Sec. There's quite a few issues with Bgp Sec. So with Bgp Sec, the router does the signing of the messages between AS1 and AS2 in this instance. Then AS2 signs onto AS3 and to AS4. And what we're doing is we'll encapsulate that original message so that these guys over here can decrypt it. So the Bgp Sec speaker will validate by checking. So if there's a role that describes the prefix, and the AS path can be validated by that chain of signatures for all the routers in the path. Oh, my thing's moved over here. Right, there we go, I can shift E that now. So there's a few problems with doing this. Because you're doing crypto on the routers, you can't have partial adoption. You can't have a hop in the path that isn't going to be able to sign. You need more hardware resources, and the vendors love this because you're now going to buy bigger routers that can do crypto. You need more CPU. You need more memory. And there's no clarity within the RFC on how we're actually going to distribute these certificates. So probably not a great thing. What about ASPA, AS Provider Authorization? Again, this is in draft. What this is doing is it's saying we're going to sign some objects that are going to bind our provider ASNs and our customer ASNs. And it's it's another attestation that I'm authorized and allowed to send these. So my upstream would be able to validate that, and so on and so forth. So you're specifying your AS path to your border, and you're saying, this is what I'm allowed to do. If we're not seeing those two hops, and we're not seeing that signature for those 2, 3, 4 hops, then we can drop the traffic. So it's a little bit, this is a simplified thing. If there's no valid ASPA for the customer, then we just continue on. If there is an ASPA with a customer AS, then we have a valid AS path. Otherwise, it's invalid. So we wind up with our very similar validation states. And you can do further reading, of course, on X509 PKIs, extensions for IP addresses and ASNs, and RPKI. Any questions so far on any of that?
Hi Dave, there is a question in the QA box.
Let me have a look. Let's fire it up. I don't have a lot of screen real estate here. I guess having many trust anchors doesn't scale up well from a validator's perspective. Too many sources of truth. Yahya Khan, always with the curly questions. It's big. it should scale fairly well. If you look at who the trust anchors actually are, right? The trust anchors are the RIRs, of which there are 5, and any of the NIRs or regional registries. So the number of trust anchors you have is fairly limited. I don't know. I'll have a look tomorrow when we run the lab, but we're not pulling a hell of a lot. When we do the initial sync, like for instance, we'll probably use RouteNator in the labs tomorrow. When it does its initial sync, yeah, that takes about 10 minutes. Okay. Subject to your link speed. You're always gonna have more than one validator because you're gonna need redundancy for this. But the lifting and the work is not done by the routers. All the work is done by your validator sitting on a box. Providing this is no worse than your web browser. So let's go see if I can do it. Where am I? Actually, no, I'll just open my machine certificates. Give me 1 second. These are all the trusted root certificates that are installed on your average Windows machine. If you think that having 5 RIRs as a trust anchor isn't going to scale, then the rest of PKI and asymmetric keying is doomed. I have issue with who determines who a trusted authority is in this particular model, but that's a topic for another day. But between that and your intermediaries, you're maintaining a lot of trust anchors already. So from a validator, as long as it knows who the roots are, the roots will then tell the validator who is trusted below it. So I think it actually doesn't scale too badly. Unless someone can come up with another answer as to why or a better solution, I think this is the one we have. Any other questions from anybody whilst we're taking questions? We've got about 2 or 3 minutes before the break, so I don't really want to kick off the next section until we're ready to go. Questions can go into chat, into our doc, or into the Q&A box if anybody has anything else. No? All right. What we might do then is we might break now for 15, stretch your legs, and then we'll get into a bit of implementation. I don't know what a 15-minute tinner is, but I'm hoping Google works it out. Thank you. All right, so we'll come back in 15 minutes, and then we'll move on to implementation. So go and have a stretch, get a drink, do some yoga. So you can go and grab it from there.
Hi, yes. This is all recorded, so we'll have it online.
Yep. Fantastic. All righty. Yeah, leave side. That's fine. All right. Let's move right along. Let's start talking about the fun bit. Implementation. So It's all well and good understanding how the process works and what we can do with all this, but how do we actually stitch it all together and make it work? Step one is you have to sign and publish your rower. So first thing you need to do is go into my APNIC, activate your RPKI engine, and then go to resources, resource certification, RPKI. How about I just do it? Far more interesting. Bear with me 1 second. Let me go and log into my APNIC. And just move this over here for a second whilst I type some passwords in. Get over to this screen here. There we go. So a couple of catches. There's two things that need to happen even before you've actually, well, once you've enabled your RPKI engine that we don't detail in here. One of those things is you have to make sure that you have got two-factor authentication set up on your account. Otherwise, we do not allow the signing of rowers. The other thing is it's a separate permission that your corporate contact will have to assign to you if you are only a technical contact. So they'll actually have to go into the permissions and actually change your user so that you can sign resources. Okay, embiggen. There we go. So let's go into our resource manager. And I'm going to go to my resources. And we have our RPKI engine. So I've already set RPKI up for, or someone did at some point, well before me. But you would go in here and you would enable your RPKI. Once you're there, you would then go into your routes. So it was also back on the main page. Anybody who has actually created route objects before, this isn't very different. So I've got my list of resources here. And for me to go, and as I said, you can actually add multiples. So I've got a range of resources that we've got assigned. So I'm going to go and create a new entry. So let's say I want 61.45.248.0/24. But I also would like APNIC AS to originate that for me. So I just go in and say AS 4608. Under normal circumstances, and this is this maximum length, the MSA. So because it's only a /24, I can only assign a /24.
Your camera is okay? It's stuck.
Everything's stuck. Zoom just crashed. Second Zoom crash for the day. Reshare my screen. Right, we back to normal now? I've lost all my chat boxes and everything. Right, okay. What did we see up to? So what did we see up to before I went and hung? Is anyone actually paying attention and can tell me? Okay, cool. Thank you. Right, so I'm creating my route. So let's just say, for instance, I did want to do this, and I will actually make it for 248/23. Origin AS, I'm going to allow AS 4608, and I want to go down to maximum/24. To assign a rower for this, you click enabled. If you don't want to update your whois object, so if you, for instance, are assigning, if you are just doing a rower for a third party, you may not want to create a whois object, and you just click next. Not a great day. 61.45.0.48/23. AS 4608. Live demos go wrong. We go to max/24. No, enabled, and we go next. Then it will come up here. It will tell you what you are creating objects for. We're saying most specific announcement is /24. And then we go submit. And whilst it's doing that, we can go and have a look. We go to route requests. And it'll tell me it's doing it. And look, there it is. We can go and view that. And it's done. So now if I go back to my resources, I could have done it back on the menu, but that's all right. I go to my routes. And if I search for 61.45, there it is right at the top. So it's still waiting, it's creating it. This is done in a batch, so it could take about 10 minutes, but once you get green ticks on everything, it's all good to go. And then we done it yet. Come on. 61.45. Oh, I'm still waiting. But yes, eventually you'll get all green ticks. Couple of limitations. If you're doing B6 and you've got a /32, I think the biggest you can go down to is /36s, and it'll automatically create them all. But remember, it's creating a rower and a route object in some cases for, in that case, the 32, the 233s, the 434s, 530, the 835s, and the 1636s. So you're creating a lot of objects. So keep that in mind when you are doing this. But as you can see, it's that simple, right? Not hard. If you are in India and your address space is with NREN, you'll have to contact NREN for their process to actually do this. This is for APNIC members through the My APNIC portal. Right, so we've got our routes, been through this. There we go, I've expanded, it's now /16. It used to be, 8 bits, so it was an issue. So you can now go down quite a bit. So you can go down to the /48, but again, do you really want to create 65,000 route objects for things that you may not be originating? And then afterwards, so this link isn't going to be around for much longer. I'll discuss that when we start talking about choices of validators. But you've got a few options for actually checking that your routes are actually valid. You can also use whois, so NTT actually will publish that. I believe most of the route views, or some of the route views, I think David was saying yesterday, also publish that. So you can check in multiple places. BGPmon, same deal. You can see you get that row of validation state here. So let's talk about what's happening globally. So in our global rowers, this was done in October last year. So V4, we had 851,000 routes, about 158,000 rowers signed. We had 206,000 valid routes with 637,000 unknowns. There's a lot of unknowns out there, so it's still a lot that are not signed. We look globally. So these are invalids. So within APNIC in V4, there are 2,802 invalid V4s and 956 invalid V6. We look at the RIR specific ones, NREN, 163 invalids there for V4. CNNIC is a whole other discussion. JPNIC, nice and tidy as I'd expect. So there are invalids out there still. So things to think about when you're actually creating your rowers. Make sure that your value covers your announcement. So that's on a couple of things. So that's your max length. If you are not advertising every /48 in your /32 V6, don't go and publish rowers for them. Why do we say that? Because you are creating yourself an attack surface. Somebody could spoof your origin AS for something you're not routing, and guess what? It then looks valid. So only create announcements for things that you are actually routing. In fact, when you first go into the rower tool, it will actually pull what is already seen from APNIC standpoint in terms of what you are advertising. And you just go and check all the boxes and go create those rowers. Done. So that makes your life a whole lot easier. But don't create rowers for address space that you are not originating at that point. So only create the rowers for things you are currently announcing in BGP. That brings up the point of maintenance. So if you then go and add a new prefix, don't forget to create the rower. Rise of the Invalids. This is a blog that Jeff Houston put out April last year, I think. We've seen a rise of invalids. As more people are signing their rowers, they're doing it incorrectly. We're seeing this an awful lot. Max lengths. We have a look at V4 is obviously the most dominant one because not enough people are doing V6 to make a change or much of a change. That needs to change. On the plus side, this bit's going down. So the invalid origin AS, but it is kicking up a little bit, but it has dropped off significantly from where it was. Invalid AS is going to cause you a lot of pain with your upstreams if they're doing route origin validation. I've spent a lot of time over the last probably 4 or 5 months working with multiple ISPs, trying to reach out to their downstream customers who are non-responsive, telling them that they're doing invalid origin AS, and guess what? They're going to be dropped. So we've spent a lot of time working with a lot of ISPs to get this sorted out. So make sure that your max lengths are correct. Make sure your ASs are correct. Run your own RPKI validator. Don't rely on somebody else's. It's really not that hard to run. There's plenty of them out there. So Dragon Research RPKI Toolkit, they are looking for maintainers. It hasn't been updated in some time. RIPE validator. RIPE have slated that for execution this year. I believe it's good till July, and then it'll die a natural death. RouteNator from NL Labs. We'll be running that up in the labs tomorrow. That is my validator of choice. Release candidate 2 is the recommended version right now. We also have Octo, Go Router, which is Cloudflare's, and Fort from Nick Mexico. Choosing your route validator is going to be almost like a religious discussion for some people. The problem we have with a lot of the validators is their logic. If they're running in strict mode and they have a bad manifest, they may drop the entire manifest file. Or if they have a bad signature in one particular entry, they may drop the whole manifest file. So considerations to be made when you are choosing your validator. So securing the router session. So this is between you and your router and your validator. You either just use plain text, providing you're staying within your routing domain. You have other authentication options, so SSH, MD5, IPsec, TLS, etc. That doesn't change anything. Things to also think about is when your router session fails. Based on your defaults, your default knobs, so make sure you always check the default knobs in your routers. 3600 seconds, so what's that, an hour. iOS XE, 5 minutes. The RFC minimum recommendation is 600 seconds, so 10 minutes. So based on that, if your router session fails, what will happen is within your router, once that session goes down, once your cache actually expires, everything becomes defaulted to not found, including those invalids you've been dropping. So make sure you do have at least two validators sitting there. One primary, one secondary. People always ask me, should I run RouteNator for one and RIPE for the other? Refer back to the previous question about different validator logic. If you're going to run one, make sure your second one is the same and you've got consistent data on both. So enabling this on your routers is really easy. Do it on your border, peering, and transit routers, right? Closest to the internet. On your eBGP speaking routers. Know all of your platform's defaults. This is a bit of a real big gotcha. iOS XE will not use invalids for best path selection unless you tell it to. It will drop them straight away. So if you want to do traffic engineering rather than dropping, you need to enable that. So we talked about what we could do in terms of what do we do when we get these routes. So we could create something around local pref. So if a route is valid, we give it a local pref of 200. If we're coming up with a not found, we leave you at default at 100. Or if we get a match RPKI invalid, we could either set local pref to something really low, or we could just drop it. Depends on how you want to roll the dice there. Then all you need to do is apply the route map to your BGP session. And don't forget to do it for both address families. If you've got V4 and V6, do it for both. So these are all Cisco examples. Here's Juniper. Establish your session with your validator. So do your group declaration, set the session, refresh time, the port it's listening on, for the validator's listening on, and the address of the validator. Then go and define your policies. and either local pref or drop. Bad news for MikroTik out there if you are running it at this point in time. RPKI is not in ROS 6 at all. It's been put into ROS 7 at last beta 3, I think it is, 7.1 beta 3. It still isn't working. What's currently happening with it, based on the test I did a couple of weeks ago, was it would just mark everything, depending on how you built your filters, it would mark everything as that. So if you put invalid as your first filter match, then everything will be marked as invalid. It wouldn't actually match the state. But if you do an RPKI verify with the router session, everything looks fine. So MikroTik are aware of that and they're still working on it, much like the rest of router OS 7. So how do you verify? iOS is a bit limited. So you can do a show BGP IPv6 or show BGP IPv4 unicast RPKI, and you can either see the information on the server or you can see the table entries. You could probably do a pipe I and filter it a bit, but there's not a lot you can do. This is what the output from checking your router session looks like. So you can see that you have your neighbor there, you got your connection attempts, and you can see that it is established, and that's about it really. There's not a lot of info. Oh, prefixes. How many prefixes are actually you're pulling from your validator? You can see the RPKI table, which just spits out a list of everything you are pulling from your validator and sitting in your cache. Keep in mind, this is more memory you need to have on your routers. So you want to check your routes. Here's a couple of examples. So we do a show IP BGP IPv4 unicast for this prefix here. And what we have here is AS17660, and its RPKI state is valid. Same for, well, for this one here, we have a not found. There is no rower for that particular prefix. So that one comes in as not found. Junos, we can validate the session with our router, with our validator, sorry. State up, a few flaps there, uptime, and number of V4 and V6 records, all in one command. You don't have to run two commands, it's Juniper. And you can also have a look at the session on a per validator state. So if you've got more than one validator, you can actually check each one. You can actually see the RPKI cache. Pretty much the same, not much difference on the output, apart from the fact that you get to see everything all at once. You don't have to specify V4 or V6. And you can filter per origin ASN. All of you Juniper people out there will love that. You can check the routes, check the validation status again, and it still reports it. So you're getting the same info, or you're getting better info out of Juniper, quite frankly, than you are out of Cisco at this stage. So what about pushing this data down to our iBGP peers? So we want to make sure that not everybody, or not every router or BGP speaking router in our network needs to have a router session. Like I said, it's all your eBGP talking out to the big bad world, whether that be to your downstream customers or out to your upstream transits, or even on your IX routers, your peering routers. So you have to make sure that everybody has the same information. So we're relying on a non-transitive extended BGP community. What this does is within our BGP session, we have this community, and we have the validation state being sent across to our IBGP neighbor. If we've got a valid, comes up as 0, not found 1, and invalid 2. And you have to enable it on your sender and your receiver. So make sure both routers are enabled. So this is the sender with one router session. We do a send community both. So we're sending both community types. And we are announcing RPKI state. Again, do it for both address families. And on the receiver, again, we have to enable extended BGP communities, and we just say announce state again on both communities. If it's not configured, all prefixes received from the IBGP neighbor will be marked as valid. So make sure that unless you're dropping everything at the border, mark it as valid. Junos, same but different. Junos, we just do the community add, origin validation state for all 3 types. So we have to specify route validation in our policy, or that's our policy statement. If we see valid coming in, we're going to add that community. If it's invalid, we're going to add state invalid. And if it's unknown, we're going to add state unknown. And on Junos's side, all we need to do is actually specify those 3 again. A bit easier. So what about default routes? If your upstream is sending you a default route, that's not good because it will match everything. So if you have an invalid that you're dropping, somebody tries to talk to said invalid, it's just going to send it anyway because you've got a default route. So there's no point in having a default route. If you are running with a default route, there's no point in doing RPKI either. So think about that. If you are not taking a full table, that invalidates the possibility of even doing this effectively. So no default routes. Multi-state propagation. So this is if we are going to be using the RPKI state. So you might be going from Cisco to Juniper. There was a problem. In earlier versions of Junos, so anything lower than these guys, on the Juniper side, you'd wind up with this unknown IANA 4300. So 2 options you have. You either act on the states at your border, so you're either dropping it, local prefing it, whatever you're doing there, or match and tag them and do your own communities before you propagate, or update to a more up-to-date OS, Junos. There is another AS which gets a little bit messy, and we'll talk about AS0. What AS0 is a negative attestation. So this is a reserved ASN that says, I am not routing this. So what do I mean by that? Okay, let me bring up my whiteboard. So Dave over here on AS1234, I have 1.0.0.0/16 because I've got a lot of money, right? I decide that I'm not going to be routing my /16. I'm only going to route 1.0.1.0/24. So I go and sign my rower with AS1234 for this prefix. I don't want that ever. Even though I've got the resource, it's my address space, I don't want that being run by anything anywhere, because if I've only done that rower for the /24, somebody goes and does the 16, they can announce that because it'll be an unknown. I have no rower, no covering rower. So what I can do with that is I can say, in the APNIC portal, I'm going to originate that from AS0. What that tells all the validators out there is this is not routed space. Do not route this. The owner of this, the resource holder of this space, does not want this being routed. So you would do that as AS0. Is that clear? Do we understand what an AS0 actually does? If I don't want that prefix appearing anywhere and I want everybody who's doing ROV to drop it, I assign it with AS0. If I go and create a rower for that myself, and I actually do go and sign that, this rower here overrides that one as the resource holder. Okay? So I can do that. This bit always confuses people. So I just want to make sure everybody understands what AS0 is used for at that particular instance. Because I'm about to muddy the waters even more. APNIC, Proposition 132 came into effect in September last year. What Prop 132 does is it says APNIC will assign this AS0 rower to any of our undelegated or unallocated space. So these are resources that APNIC have that we have not allocated to anybody yet. Now, to make it easy for everybody, there is a separate TAL for this. So there is a separate TAL file. There is detail on this on a blog post that was done, I think, by GGM last year, which talks about this in a bit more detail. But this is an AS0 for our undelegated space. This does not include things like historic space. If you're sitting on historic address space, APNIC will not AS0 that space. The reason is the space isn't delegated by APNIC. We cannot positively or negatively attest to anything to do with that address space. So if you're sitting on historic space, that's not an issue. What also is an issue for you is if you have got historic space that isn't in your account, you can't sign a rower for it either. So you may have to go through the process to do a claim for that historic space. So that's something else to think about as well. So do not confuse Prop 132 AS0 with your AS0. Your AS0 is you saying, I don't want this routed. Prop 132 is unused, unallocated reserve space that we don't want routed, okay? They're two very different things. Let's have a look in a bit of detail. I pulled these stats on Monday. It's pretty straightforward, just what we're looking at here. India, yes, you've got the highest number of prefixes. And you're sitting at about 37% sign, which is great. But you've got a lot of unknowns still. Now, I understand that, yes, now this is only APNIC space. So this is not including NREN. Oh, no, this is APNIC and NREN, sorry. So this is both. This is APNIC and your regional registry. So this bit here is the one that concerns me on everybody's. Invalid max length. This is so easily avoided. If you've got a covering rower for your aggregate, so you've got a /22 and the rower is correct for that, but you're originating a /24, Any traffic engineering you're doing is not going to be working. The second it hits anybody doing ROV, it's going to be dropped. Okay. This one, if you were at the NOGS one yesterday, we brought this up. Bataan Telecom, yes, there's only 46 prefixes there, but they're all valid, 100%. Maldives isn't far behind. There's one prefix left that still isn't signed. Nepal, doing a great job. No invalids. Love it. Just need to work on these guys. Pakistan, typical max length type issues, but you almost hit 90%, so you're getting close. Just need to work on those other 537 over there. I'm sure Yasir will be reaching out to people soon to get that stuff sorted out. Afghanistan, all things considered, doing quite well. Bangladesh, come on guys. You're at 91% signed, but you're at 16% invalid. And most of it's this. Most of it's max length. Be mindful of what you're originating and what you're signing, right? This may well just be new address spaces have been added or new addresses have been moved around for TE purposes and someone's forgotten to do the rowers. But 978, 145. Why do we see that one? Okay, this is a little bit different. I had a bit of a dig into this. Anybody who does, let me just bring up a whiteboard. So look at your architecture of your network. You might have a router out here. And this is your transit AS. And you might have a couple of access routers with a different AS. So you might have an access AS and you might have another AS for your mobile network. You need to think about where the addresses and the devices are, where that address space is originating from. Are you originating those from AS1? Or are you actually originating that address space from your access ASs? If you are originating it down here and your AS path looks like 2.1 and 3.1, then that needs to be in your rower, not this guy, right? Same goes the other way. You might have a customer who has their own AS. They have their own address space, but you, for whatever reason, are originating that. Then your customer has to update that and have you as the origin AS. That aside, that could potentially be breaking other things out there. The route objects aren't even the right way around. You may have upstreams and IXs anywhere dropping traffic because, or dropping prefixes because you don't have route objects that are correct. So these are things that we talked about earlier that break the way the traffic flows. And these are considerations you need to do when you are signing your rowers. So it's great to see that for the most part, South Asia has this pretty well sorted out. Almost, so close. Why is that not working? There we go. So if we can get someone working on these, somebody working on that, and we're getting a fairly good way in South Asia of getting this stuff cleaned up. So make sure you sign your rowers. That's what this is all about. Signing rowers, doing validation. Any questions? Not seeing anything in Q&A.
No questions.
How to educate them about ROA. Fahad Ahmed Khan, how to educate them. Any specifications to share with them? Absolutely, tons. You could send them all the RFCs, but that would probably mean nothing to most of them. If it's from a customer side, talk to their technical people. We have, odds are they're going to be a member, right? They can come to our training. We run RPKI training quite often. In India, Anurag is actively going around trying to get ROA and RPKI awareness up. In Bangladesh, I know Simon and Awal are doing the same thing. So there are options locally. So reach out to those, reach out to us. We can do TA, we can do technical assistance. It's getting this stuff sorted out, even if it's just doing ROA signing. We get ROA signed and signed correctly, then a lot of this stuff, let me just tab back over. A lot of this stuff goes away. I'd like to be at SANOG next year and see, realistically, I reckon I can get these to 100% by next year. How good would that be? India, like I said, you guys have got a lot of address space. You've got a lot of address space, plus you have a regional registry that needs to work with this as well. So there's 2 points of call in India, so it's a little bit more complex. But just because you can't do route origin validation doesn't mean you can't sign your resources. But like I said, the main thing is these guys here, making sure that your signing matches your BGP. If in doubt, go to something like route views, punch your prefix in and look at your AS path. Make sure that your origin AS is the one that you are putting in your ROA. The other thing I haven't covered, like I said, this is only APNIC for the bottom 6 and APNIC and NREN for the top one. There is a lot of other address space I notice around. There's a lot of Afrinic, more than likely leased address space within South Asia and originating from South Asia. Because Afrinic has no inter-RIR transfer policies at the moment, as in they're not allowing it, you can't transfer that space anywhere. So anything you need to do with ROA, you have to do with Afrinic. And if you are leasing that space, you have to go and talk to whoever you're leasing the space from. But I have not included that in my stats because I've got no control over that, and some of you possibly have less. So I'd like to see by SANOG next year, this section here, all at 100. I'd like to see this at 100, but I'm being realistic. I think this is achievable. Sri Lanka is close. Nepal is close. Maldives, yeah, so close. Pakistan, like I said, I know Yasir is working on that. Afghanistan, I'm not sure how we're going to go about that one. But Bangladesh, if you guys could clean up your invalids, that would make me a very happy person. I wouldn't see it in my reports every day. Anybody unclear about the actual process we go through for actually signing our ROAs? Absolutely anything here that is not clear. This is, like I said, this stuff is, the signing part's the easy bit. The validation bit, if you're doing the labs with me tomorrow, you'll see that is also quite easy. So now is the time to ask me these questions, not in the middle of labs tomorrow. Nothing? Okay. In the time we have remaining, I would like to try and start sorting out who is actually going to do the labs tomorrow. Let me open this guy up, because we have a very limited amount of time tomorrow to do labs, and I only have a limited number of resources. So can we go to the Word doc, which I'm linking back up in here? If you are going to do the labs tomorrow, not maybe, I might do it. If you are definitely going to do the labs tomorrow, go to that link I've just posted in chat and start filling your names in. I've got 101 people in this session from what I can see on my list. Excellent. Find some blank space. This way I can make sure that I've got enough stuff running that you guys can all do this. So Dibia and myself will be running these labs. We'll be doing it interactively with you, so you can actually see what we're doing, see the expected outcome. We can help troubleshoot if we need to. I think I'll delete that. Oh, I published earlier. Otherwise, Tashi will get shirty with me.
Please type your full name so that we know that.
Yes, we know who it is.
Yeah. Yep.
That'd be really good. Doing some housekeeping whilst we're going. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 people want to do labs. Is that all? So you're all experts on ROV deployment. Oh, there, cool. I should make my life easy tomorrow. There's only 11 people doing it. All right, any other questions before I wrap this session up? Any concepts you need me to bounce back onto at all? Nope. Fantastic. All righty, so tomorrow, ensure that wherever you are going to be doing the labs from, you have got SSH access allowed to the outside world. Okay, make sure that SSH is not filter. Lab setup. Now I'll do a quickie. Anybody who's been to any of our training in the past, anyone who's been to any of our training in the past knows that we have you sitting over here on your device. We will have a nominated jump box sitting here. You will SSH to that jump box. Then you will be given a Linux machine to configure your validator onto. And then for the second part of the labs where we'll be actually configuring routers to do this, you'll also be given a router. So the reason we say make sure you can SSH. If you can't SSH to that jump host, you can't access the labs. We've got allocated for tomorrow 2 1-hour sessions for the labs. The lab guides are in the wiki. So you can have a look and read the lab guides ahead of time if you choose. I'll post that up again for those that may have missed it. Excellent. So that is now on the chat. So you should be able to grab the lab guides from there. Like I said, we will actually take you through this. I'm not just going to throw the lab out there and let you do it. We'll actually walk you through the lab so you understand how it works and how it's done. Due to time constraints, we'll probably only install the Routinator. We'll probably only install Routinator. If we have time, maybe a second one. Like I said, we definitely don't do right because it's being deprecated. It's being sent out to pasture. With the second lab, hopefully you're comfortable with Cisco iOS because we'll be configuring Cisco routers. So put your Cisco hat on, make sure your Linux hat is on, and make sure you can SSH. All right. Last call for questions. Going once. Going twice. Done. All right. Thanks everybody for your time today. We'll see these people tomorrow. If more people join overnight, that's fine. I have no problem, but I need to know tomorrow how many people are actually going to do the labs. Just keep adding lines on. I can spin up about 1, 2, 3, 4, 4, 3, 5, 6, 7. I can spin up about 32 users worth of ROV, and yeah, lots for router and for validator installs. Lab assignment, sorry, I just saw a question there. Yep, just fill it in on our Google Doc, oh sorry, our Google Doc, our Word doc. I've just posted that back up there. So click on that, scroll down to lab assignment, and you will be able to add your name to that list. I said, if you run out of space, just keep adding rows to that table. All right. I'm 10 minutes ahead of schedule, so how do you want to handle this, Dibia? Do you just want them to have what break are we supposed to be on now?
So I think a few more names are coming up in the lab assignment, so we can just wait for that one.
Yeah, cool.
And we can go for a break actually.
Yep. I'm just gonna have a look and see. Where is it? Let's see what we're supposed to be doing now. Supposed to be on lunch break, so you get an extra 10 minutes for lunch. Make sure you're back in time for Paresh at 1 o'clock.
Yes.
Absolutely. Cool. Okay, everyone. Thanks very much. And we'll see those of you doing labs tomorrow. Have a good rest of day.
Welcome back, everybody. For our next tutorial session is on segment routing, which is very exciting tutorial. So I hand it over to Paresh actually, and then start right away.
Thank you very much, Dibia. Let me share my screen. I trust all of you can see that.
Perfect, Paresh.
Excellent, Philip. Thank you. So welcome everyone to this tutorial on segment routing. So before I start, a quick introduction. My name is Paresh Khatri. I work for Nokia, and I'm actually based out of Brisbane, Australia, where a lot of the APNIC folks are based as well, which is somewhat handy. So I am looking forward to this tutorial on segment routing. Normally, I present this tutorial over 3 hours. So I'll be trying to condense some of this so that we can cover a significant chunk of material in the 2 hours that we have available to us today. But I'm not quite sure how it's going to go. I may overcompensate and finish really early, or on the other hand, I may not be able to do that. But in any case, I think what I'll do as part of this tutorial is concentrate on quality over quantity. So I will not skimp on any explanations that I see fit. And then you have the whole deck if you, well, once I've finished with the presentation. And if you do have any questions at the end of it, we can take it at the end of the session, or you can contact me offline once the session is over. I'll periodically look at the Q&A, and if you do have any questions, then I'll try to address them there. If not, we'll cover them at the end of the session. So let's get straight into it. Actually, you know what? I mean, that's fine. We'll go straight into it. So segment routing. I'm sure some of you have heard about segment routing. It's a concept that's been around for about 7 or 8 years now. So it's not new per se, but it's new from the perspective of production experience. Over the past few years, particularly with the introduction of networks that are designed for more on-demand, cloud-based 5G kind of services, we see that a lot of operators have decided to move to segment routing as an alternative to the traditional ways of building carrier grade networks. So there's a lot of interest on this in the market today. So now the way I've got this agenda structured is I'll give a bit of an introduction to the technology of segment routing. It necessarily involves a bit of terminology, like a lot of new protocols and technology out there. But what I'll be doing is trying to explain it through examples as well, so that it kind of has a bit of context, that it's not just a dry presentation on theory. And then we'll look at some of the use cases and the applicability of segment routing. And I think this is the interesting bit, because it kind of brings forth the real benefits of segment routing, and will give you a better appreciation for why operators are adopting segment routing in their networks. And then finally, we'll look at deployment options, time permitting, but we look at how we can actually deploy it in both greenfields and brownfield kind of scenarios. So let's get into it. Now, like I said, there's a bit of complexity to learning any new technology. So what I'm going to do here is give you a bit of a sneak preview of what segment routing is, and then over the course of the next hour, we'll go through some of the concepts in a lot more detail, so that you can solidify your understanding of the stuff that I cover at a very high level now. So the big shift that has happened in IP MPLS transport networks over the past few years, with the advent of SDN and NFV, as Santanu actually covered the other day, is that things are becoming a lot more dynamic. And if you look at how we designed networks in the past, where we had that hierarchy of access aggregation and core and a very fixed physical location for the service edge devices like BNGs and provider edge devices and so on, that model is not really suitable for networks of today. That model was applicable when we had a very simple data flow, right? There was content coming from the internet or very centrally located data centers and going out to the access networks. So it was very, east-west, and it's predominantly downstream. But that's not the case anymore. We look at these cloud-native architectures, the advent of 5G and so on, and we see that the whole network has become very dynamic, because you now have this whole concept of virtual endpoints that are delivering traffic or services. And these virtual endpoints are not fixed. They are dynamic. They could be anywhere in the network. They could be virtual machines and containers spun up on demand, torn down when you don't require them. So the whole traffic model has now become very multi-point. So it's not as point-to-point as it was before, which means that within the IP routing space for carrier-grade networks, we've got to change, because we need to be able to handle this dynamicity, and this is not something that we can handle in a manual fashion as we did before. So when we look at these carrier-grade networks, that are built by large telcos, tier ones, tier twos, a lot of ISPs out there as well, a common thing out there is that they use MPLS, MPLS within the core of the network. And it's fair to say that the de facto way of implementing MPLS is using protocols like Rsvpe and Ldp. And they've been great protocols, don't get me wrong. We've been using those protocols for about, more than 20 years now, and they've served us well. But the challenge we're running into now is that they are not able to scale for this on-demand cloud environment. They were never designed for this, because we now require the ability to do traffic engineering on a per flow basis. So having that coarse traffic engineering capability that we have with Rsvpe is not sufficient. We'd like to be a lot more granular in terms of how we do traffic engineering. And so Rsvpe doesn't scale. it just will not scale to handle the thousands, the tens of thousands, potentially millions of flows that we have in the network. So we need to look at a different way of actually addressing that challenge that we have. So the solution to that is, or at least a part of the solution to that, is this whole concept of segment routing. And it's key to understand that segment routing is a paradigm that is based on source routing. Now, you guys know that we in the IP routing field are not comfortable with source routing. And I remember back in the day when I was just starting out in the networking industry, one of the first commands that we entered was no IP source route until it became a default. And we did it for good reasons, because source routing into the internet is a huge security risk. But when we talk about source routing in a segment routing context, it's confined to within an operator's network. This is not source routing within the internet infrastructure. And so we've got a lot more control over source routing. Now, why is source routing important? Source routing is important because it does one very key thing. It puts the responsibility for how traffic is routed, how packets are routed in the network, on the ingress node, which is very different to how we do things in general in IP networks and MPLS networks, where we do destination-based routing, where every router has to look up a field, be it an IP destination address or a MPLS label, or any other field that it's using in order to route. We take this away from the midpoint of the network and we put that intelligence in the packet itself. Now, an immediate benefit of doing this is that we are deloading the network. So the network does not need to have detailed information about how packets need to be routed. And this is key to how you achieve this scale within networks to be able to do things on a per flow basis. So what segment routing does is it actually puts this routing information inside the packet itself, inside the header of the packet. And as the packet makes its way from ingress to egress, every router along the way looks at this and is given specific instructions on how to route the packet. So I will not go into details here. This is just, like I said, just to give you a sneak preview of what it does. We'll go into a lot more detail as I go along. But the two key points to take out of this is that segment routing is based on the concept of source routing. The routing information is encoded in the packet itself, in every single packet, so that the core of the network, the transit routers, do not need to make complex routing decisions. And by doing that, we're able to scale the network a lot more, a few orders of magnitude more than we could have done if we were not doing source routing. Now, a very key thing that complements segment routing is SDN. Now, I mentioned that we put the intelligence, the routing information in the packet itself. So the question here is, how do we get that routing information? If you're moving it away from the transit routers in the network, where do the ingress routers get this information from? This is where SDN comes in. Now, if you couple a segment routing implementation, so your router is running segment routing, with a central SDN controller, now then you have the ability to make these sort of path computation decisions at this SDN controller level. So they're being done at a central point in the network. And then the SDN controller communicates with these routers, your provider edge routers in your network, and tells them what to do with every single flow, what information, what routing information to put in each packet so that it can do its bit. Now, there are a number of benefits to this. One of the benefits is that instead of having a limited view of the network as every router in a distributed routing network does, we now have a global view of the network. And this is important when you think about things like IGPs. we confined to the information that we can glean from the LSAs and the LSPs that are in the area that we're in. Anything outside of that loses topological information. Having a controller that is sitting on top, like an Oracle, has a complete view of the network, actually puts a lot of power into that system. So by doing that, we're able to build these end-to-end paths that cross multiple IGP areas, multiple IGP instances, even across autonomous systems, and be able to map out a path that meets SLAs. And this is key. So on the first day, we heard from Dhruv on Ietf network slicing. And one of the things that he talked about was SLAs, and specifically SLOs, or service level objectives. This is something new that we're getting in IP routing. We've always built networks that provided virtualization and isolation and so on. But the level of SLAs that we provided, guarantees around latency and packet loss and availability, were not quite there. We'd provided at a very high level, but to differentiate it on a per flow basis is something new. By having an SDN controller that has a complete view of the network, we're able to actually take this up a level and be able to provide this differentiated service to different flows. So that's important. Now, by having that global view as well, the controller can now make more intelligent decisions about alternative paths. So in the event of failures, what is a better path to take? We know that when we have things like routing based on IGPs and so on, we have things like micro loops and so on, while the network reconverges. It's an outcome of the different routers in the network having different information because they haven't converged yet. By having an SDN controller, we can get rid of things like that because we have better visibility of the network. And so there's a whole impact on resiliency that we can get by combining SDN with segment routing. So that at a very high level is segment routing. We're now going to want details on segment routing. So before I do that though, I'd like to dig a little bit deeper into the shortcomings of the current protocols that we have, and in particular, LDP and Rsvpe. So for those of you who are running LDP and Rsvpe, you're pretty familiar with this. For those of you who are not, this should be a quick recap. There's a reason we use LDP. We use LDP because it's simple. It's pretty much plug and play. You turn it on and it does its thing. But it doesn't give us traffic engineering. It's a protocol that gives you basic MPLS capability. We've extended it over the years, so it can do things like fast reroute. And we do it using something that we call LFA, loop-free alternates. So with every primary LDP path or next hop, we're able to associate a backup. We call it loop-free alternate. So if the primary path fails, we can immediately switch traffic on to the backup path. So we've got that. So we've got fast reroute with LDP, but we haven't had traffic engineering, and we don't have traffic engineering for LDP. So what we've done is, to scale networks, we've combined the two. We've done hierarchy, as we typically do on IP routing networks and architectures. We've done things like tunnel LDP over Rsvpe, so we get the best of both worlds. And we've done things like seamless MPLS, which is a technique that is becoming almost a de facto in MPLS networks all over the world, where we once again do this divide and conquer approach using BGP in this instance. So we use label distribution using BGP, so RFC 3107 kind of architectures. Once again, hierarchy helps us to scale. So we've done a lot of that, but the challenge remains one of scale. As I mentioned, with the advent of 5G in particular and cloud-based services, there's a greater desire to differentiate on a per flow basis. And we cannot really do it with any of these mechanisms while achieving specific SLAs for different types of flows. So it's been time to take, no, it's time to take a look at what else is out there. So very quickly, before I go into segment routing, just a comparison of LDP and Rsvpe. So LDP is a multi-point to point construct. So we can have multiple ingress nodes sending traffic using the same, you call it an LSP to an egress endpoint. With Rsvte, it's a bit more complex. It's point to point. So for every pair of communicating nodes, you have to signal an LSP. So by definition, that makes it a little bit more complex. LDP relies on the IGP. So if you want shortest path first forwarding, it'll do the job. If you want to do traffic engineering, not quite. This is where Rsvpe comes in, where we enhance the IGP with traffic engineering extensions so that you're able to actually do more sophisticated routing on using things that go beyond hop counts and IGP metrics and so on. So in terms of label allocation as well, this is actually quite significant for segment routing. With most of the applications of MPLS out there, label allocation is locally significant in that labels are only significant to the router that is advertising them. This is where there's a bit of a paradigm shift with segment routing, where we talk about globally significant labels, and I'll come to that shortly. So traffic engineering I've spoken about. LDP scales very well. There are networks out there with tens of thousands of nodes running LDP, running just perfectly, because it's a very simple protocol. It scales very nicely. Rsvpe, on the other hand, has an n-squared scaling problem. So that rapidly goes up, right? So if you've got 100 routers in the network, you're looking at 10,000 LSPs. That's a lot. And so it means that it rapidly runs into issues where the network just cannot grow any further without subdividing it. There are multicast extensions for both LDP and Rsvpe, so they both do multicast. IPv6 as well was late in coming to both LDP and Rsvte. LDP pretty much complete, Rsvte not quite there yet, at least in terms of implementations. So they're all lagging a little bit. So you can see that the choice between LDP and Rsvte has not been always very clear. And in fact, a lot of operators will run both LDP and Rsvte in their networks in order to address specific problems that they have. Right. So what problem is it that we're trying to solve here, right? I've said this a few times, so I'm sure you've got this. Scale. Simple as that. We need to scale the network in order to achieve this granular traffic engineering. Rsvpe is really the only solution that we have for traffic engineering. And as you heard, it doesn't scale. There is no concept of LDP-TE. There were some initial efforts at doing traffic engineering in LDP, but they never got anywhere. So it's just Rsvte. Now, as we said, Rsvte has been successful. It's been out there for 20 years, 20 plus years. The thing about Rsvte is also that it is a source routed protocol, right? And we haven't had any issues with that. It's source routed because the path is signaled by what we call the ingress router or the head end router from a, in traffic engineering parlance. And this ingress router has the complete ability to settle the path all the way to the egress. It's got very strong fast reroute capabilities and traffic engineering capabilities as well. The cons that it has is that it's built on, the protocol uses what we call soft state. And what we mean by soft state is that this state expires unless it's refreshed, which means that the more tunnels you have, the more LSPs you have, the more signaling is required. And we've done things to reduce that through things like refresh reduction, but it's only up to a certain point. It does not actually reduce the amount of state that is kept in the intermediate points in the network. Now, remember, I said that one of the objectives here is to make sure that the intermediate routers in a network, the transit routers, do not carry a lot of state information. In the case of Rsvpe, they're carrying state information of every single LSP. So that's not a great architecture, right? With in the when we talk about good protocols, we talk about something called the end-to-end principle, where we confine the intelligence to the edge and keep the core very simple. That's the whole basis on which IP routing works. Rsvpe doesn't quite go along with that idea. So as we build more and more tunnels, these intermediate points, which actually have a lot of transit LSPs passing through them, become a real weak point in our network. Okay, so we now really get into segment routing proper. The primary objective for segment routing, as I said, is source routing, right? And it's really the ability, as I've stated here, for a node, an ingress node, to specify a unicast forwarding path that is other than the shortest path that a packet will traverse through the network, right? We can always do the shortest path. This is the challenges when you do not want to do the shortest path for whatever reason. Shortest path is not, oops, I apologize for that. Probably someone else trying to sell me something. When you're trying to do traffic engineering, it's trying to do something other than the shortest path. Shortest path does not mean the best path in the network. So we need to be able to specify a non-shortest path to meet certain requirements. But we want to do that without requiring state in the midpoints, right? And that's key. So traffic engineered routes that are not necessarily the shortest path, but without having state in the network. Now, this work is being undertaken under the auspices of the Spring working group in the Ietf. And the Spring working group has been in operation for a number of years now. And it's addressing a few different things. Once again, I will not go into this in too much detail, but there are a few things that really underpin what segment routing is and what is the charter that we're working towards. So one is to be able to provide this IGP-based tunnels without using any signaling protocols, but just the IGP. So what do I mean by that? It means that we need a mechanism to do shortest path routing in an MPLS network or an IPv6 network, and I'll come to that, with information that is advertised only by the IGP. So that means that we'd like to do this without using protocols like Ldp and Rsvpe, relying on the IGP alone. The second bit that they would like is the ability to do things like fast reroute. Now, this is important. People notice when services go down. Customers notice when there's anything more than a few 100 milliseconds, even a few low hundreds of milliseconds. Customers notice, and as a result, we've got to build networks that our end users that provide a very highly available service to our end users. So things like fast reroute are very important. So one of the objectives of segment routing is to be able to provide that fast reroute capability in any kind of a topology. Now that is important because with some of the efforts that we've done in terms of fast reroute, such as fast reroute for Ldp, they tend to be topology dependent. So think of topologies like rings, where there are certain ring kind of architectures where it's not feasible to provide a loop-free alternate for a path. In that, if we send traffic on a alternate path, it could actually loop back. So, it's not possible to get that 100% coverage on the failure of every link or node. A requirement of segment routing, and one it actually achieves, is to be able to provide that fast route capability in a topology independent manner. And we call it topology independent loop-free alternate. There's a few other things. Clearly, traffic engineering. This is what we're trying to solve, right? This is one of the things that we're trying to achieve here is traffic engineering in a segment routed in an IP MPLS or an IPv6 network. To be able to do traffic engineering without requiring state on the midpoint and the endpoint, the tail end routers. And the most important, one of the most important things that the Ietf chartered the Spring Working Group to do was to ensure that all of this could be done without requiring a flag day, so that operators could deploy segment routing into their networks in an incremental fashion, without having to pull down something or have a flag day, for example. So those are important. Now, that was the charter for the Spring Working Group. One of the key things that the segment routing architecture worked towards was, what data plane do we support? So I'd like to, at this point, think about the difference between a control plane and a data plane. And I'm sure most of you know this really well. But just as a recap, control plane is what we refer to for the set of protocols and things that exchange routing information. So your IGP is part of the control plane. Ldp is part of the control plane. Rsvpe is part of the control plane. So it's helping to set up information that actually helps us to route packets. The data plane is the actual forwarding of the packets themselves. And if you consider some of the different data planes that we work with, there's the IP data plane. So you've got an IPv4 data plane, which routes on the basis of the IPv4 destination address or the IPv6 destination address. And then you've got your MPLS data plane, which routes on the basis of the MPLS label. Now, segment routing has been designed to support two data planes. First one is the MPLS data plane. A very key requirement for segment routing was that it support the MPLS data plane without any modification. And this is really significant. What it meant was that we could run segment routing in any MPLS network without requiring a change on the data plane. There would be changes on the control plane for sure, but the data plane should just work, which meant that we could use existing hardware, existing software were required to do MPLS data plane forwarding. And that meant all of the mechanisms of MPLS, such as having labels, having a stack of labels, the MPLS operations, pop, push, swap, all of those could stay because the paradigm for forwarding was the same. So that was one. The second one that the Ietf Spring Working Group specified was an IPv6 data plane. Now, this is interesting because to support IPv6 the IPv6 data plane, we needed to use some of the source routing capabilities of IPv6. And so the way we could do this is with a new header. So for segment routing, there's been a new header, a new routing header type that's been specified. So this is a routing extension header, right? So it's called the segment routing header, the SRH, that's been specified for IPv6. Now, as part of this tutorial, I will focus just on MPLS, but the concepts are very similar. In MPLS, we talk about a stack of labels. In IPv6, we talk about a list of IPv6 addresses that perform analogous functions. So when I have my IPv6 example, oh sorry, Mpls examples, you could pretty well substitute IPv6 in there. Now the thing about IPv6 is that the data plane mechanism in IPv6 is actually new. So that requires new hardware and software that supports that mechanism, because source routing is not something that is implemented in this fashion for IPv6 in a lot of hardware that is out there today. Okay, so like I said, there's a bit of terminology that I've got to go through here, but my preference is, once again, to do this through example. So we'll go through an example, a sneak preview, as I see, and we'll come back to some of the terminology that goes with it. Now, what exactly is segment routing? And why do we call it a segment? In its most simple definition, segment routing is a way of establishing a tunnel between a source router and a destination router. That's it. It is a way of building a tunnel. Now, this tunnel can either take the shortest path, or it can be a traffic engineered tunnel where it's taking a non-shortest path in order to satisfy some criteria. Now, this criteria could be pretty arbitrary. It could be bandwidth, it could be latency, it could be some financial metric, it could be anything, but it's not the shortest path. So how do we actually do this? Now, take a look at this. Excuse me, I think we could get a pointer up here. Let's take a look at this very simple network. What I've done here is I've labeled each of the elements that are of topological interest with this thing called a segment. And it's, this is something that's actually key to understanding. When we are talking about traffic engineering in a network, we normally have two things to work with. You've got nodes and you've got links. By the judicious choice of nodes and links, we can specify any path in a network. Now, okay, it can get a little bit more complex, but let's just go with this simple understanding that we can specify any path in a network from point A to point B by specifying the nodes and or links that it must go through. Now, we call each of these a segment. So in this case here, R1 is a segment. The link between R1 and R2 is a segment. R2 is a segment, and so on. So all of these are segments. So I hope that is starting to sort of crystallize in your head what this whole concept of segment routing is. It's where you're specifying a set of segments that a packet has to go through in order to reach its destination. Now, as I said, we encode the information of the segments in each packet. So for packets going from R1 to R4 that need to traverse a certain path, the routing information in terms of the segments that it's got to go through is encoded in every single packet. Now, the existence of these segments is advertised via the IGP. Well, and I guess there's only two IGPs that we work with these days, right? That's the link state ones, ISIS and OSPF. And we've got extensions to these protocols that allow us to advertise segment information in the network. Okay, so let me sum it up. Segment routing is about building a tunnel from the ingress router to the egress router. The tunnel is information that is encoded in the packet itself. And that information is really a list of segments that the packet's got to go through as it makes its way from source to destination. These segments are nothing but nodes, or I should say, sorry. These segments are nothing but identifiers for nodes and links that it must traverse. I'll just do a quick check, see if anyone's got any questions here. Okay, it doesn't look like anyone's got any questions, so I'll keep going. Oops, I've gone too far. Okay, right. Now, how do we actually encode these segments in the packet? So I've said a multiple number of times actually that the routing information is in the packet itself. So what form does it take? Now think MPLS. In MPLS, what do we use to route packets or switch packets? We use the label. Now MPLS has the capability to have multiple labels in every packet. We call it a label stack. So here we have a ready-made mechanism to encode this information. So in the case of an MPLS segment routed network, the routing information is encoded as a stack of labels. So I've got an example here. So you see a packet. Now the packet, okay, look, think of it as an IP packet. And you've got a stack of MPLS labels. So 1001, 37, 1001. The top label is 1001. So it's a stack of labels that is actually encoded in the packet. Now, I spoke about segment routing over IPv6. We call it SRv6. In that case, that list of segments is actually a list of IPv6 addresses. And this is encoded in that IPv6 extension header that we call the segment routing header. So instead of having a list of MPLS labels, you'd have a list of IPv6 addresses. But apart from that, no, the paradigm is still pretty simple. So the way to think about this label stack is that it's a set of instructions. The ingress router is giving a set of instructions to the rest of the network on how to forward the packet. And that's cool, right? Because we are within a private network. So this is not like you're getting information or instructions from someone external to the network. These are trusted entities in the network. So they are giving instructions to the rest of the network on how to forward the packet. Now here, I think it's very instructive to look at an example. So let me take you through this. And we'll start with the left example. Now, this is an MPLS example, as I said. It's just a lot easier for me to type in MPLS labels than IPv6 addresses. So you've got a provider edge device here, 1, that is communicating with provider edge device 2. Now you see that I've got something called a node SID. What a node SID is actually, before I say tell you what a node SID is, let me tell you what a SID is. A SID is just a segment identifier. So I spoke about 2 types of segments. You've got your nodes and you've got your links. They have to be identified somehow. Now, in the context of MPLS, they're identified using MPLS labels. So the label is representing the segment identifier. So in this network here, every node assigns a segment identifier for itself. So we call the nodes SID. So it's the node SID. So PE2 has a SID of 800, PE3, 400, and so on. So all of these are representing a label that is the segment identifier for the node. Now, a difference in segment routing compared to MPLS, LDP, and Rsvpe is that this segment ID in the form of an MPLS label is globally significant. So all of the routers in the network will recognize that 800 actually belongs to PE2. This would not be the case with LDP. So for example, if LDP, if PE2 assigned a label of 800 for PE2, P3 may well assign something different for PE2. And by the time we get to PE1, it'll be something completely different again. With segment routing, it's the same. And that's part of the reason for the simplicity of segment routing. So what do we do with this, right? Now, having a SID for PE2 of 800 means that PE1, in order to send any traffic to PE2, only needs to put a label of 800 on its packet. And it knows that it'll make its way to PE2 because it's the globally significant node SID for PE2. So what it does is a packet comes into PE1 and it's destined for PE2. Now, FEC here stands for a forwarding equivalence class. For those of you who are familiar with, Mpls, that's an RFC kind of 3031 concept. A forwarding equivalence class is already a set of packets that are forwarded in the same way. Now, in this case here, the forwarding equivalence class is for the, say, the loopback address or the system address for PE2. So we get a packet for PE2 and we push a label of 800 on it because we know that 800 is the label for PE2. So P1 sends it out to P1. What P1 does is it swaps. Remember, we're doing the same MPLS data plane forwarding as we've always done. And that's why we're able to reuse all the infrastructure for MPLS. And so we know that at a transit node in MPLS, we do a swap. But in this case, we're swapping label 100 for 100. So we're not actually changing the value of the label, but the operation is still being performed. And we're doing this because the label is globally significant. It goes to P2, it does the same. It goes to P3. Now, P3, if you're using MPLS networks, would have the option of doing what we call a penultimate hop pop. A bit of a mouthful. What it means is that, because it's the next to the last node before, it's the last node before it hits the ingress, the egress node, there's no need for the label, right? It knows where the packet's going. So it can optimize things by removing the label. But I don't want you to focus on that. This could well have been a scenario where we're not doing PHP at all, and it's sent it with a label of 800. The point here is that you put a single label on it at P1, and it's enough to get us to PE2. So a very powerful mechanism. Now, let's think about how is this better than LDP or Rsvpe. If you think about it, the label values that we're using here are globally significant label values. So if you create a tunnel, so to speak, between PE1 and PE2, you would be using the same label regardless of which tunnel it was, right? So you'd still be using the label of 800 for PE2. So that means that the amount of state in these routers, P1, P2, and P3, is confined to the number of nodes in the network. You're not having different SIDs for different tunnels, which means that now you can build lots and lots of tunnels, thousands of them, that all use the same forwarding paradigm because you're using a single set of labels. You're not having new, unique, locally significant labels for every tunnel that you have. So that's how you can actually build this very large network that does differentiated forwarding on a per flow basis. Now that's a simple example. The next example that I want to cover is where we're using both nodes and links as segments. So remember I said two types of segments. You've got your nodes and you've got your links. Now we call the segment identifiers for the nodes node SIDs, and we call the segment identifiers for the link or the adjacency SIDs. Now the adjacent SID is actually no different. It's still an MPLS label, but it gives you a little bit more control over how packets are forwarded. So in this case here, let me talk you through this. It's a slightly bigger network than we had before. And so each of these nodes has a node SID, as it does in a segment routed network. In addition, we see that we've specified an adjacency SID between P2 and P5. So for this link here, we have an adjacency SID of 1003. Now in a real segment router network, there'll be adjacency SIDs for all of the adjacencies out there. For the sake of simplicity, I'm only showing you the one that I'm interested in here, which is 1003, the link between P2 and P5. So here's the thing. In this network here, assume that all of the link costs, your IGP link costs, are identical, which means that if you had to send traffic from P1 to P2, you would have two equal cost paths, one that goes over the upper set of links and one that goes over the bottom set of links. But you would not have traffic going through these two links. Now assume that for whatever reason, you have maybe you have a flaky link between P2 and P3, and you want to avoid that link for traffic between P1 and P2. How do you do it? So here's how you do it. P1 builds a packet with an MPLS label stack that has 3 entries in it. So these, at the top of the stack, you've got an entry that says 300, you've got 1003, and 800. Now here is where it's actually really important to once again think of this whole thing, the concept of segment routing as providing instructions to the network. The way I read this is P1 is telling the network, first, take me to the node that has a SID of 300, which is P2. And take the shortest path. Take the shortest ECMP aware path to it. Once you've got there, then take this link. I want you to use that to forward the packet, which is the link between P2 and P5. Now, once they've done that, I want you to take me to 800, which is P2, and use the shortest path to get to 800. That's what it's telling the network. And the network will oblige. This is how it's going to work. So P1 sends the packet. Now, the reason I've shown 300 is because that is a top label. The network is always routing on the basis of the top label. It gets to node P1. And remember, it's going to do a swap from 300 to 300. So the packet doesn't really change. It's still routing on the basis of 300. Why is the 300 still there? It's because we haven't reached the node with the SID of 300. It gets to P2. Now here's where things get interesting. Because 300 is P2's node SID, it actually pops that label. And it then looks at the next top label, which in this case will be 1003. Now that is what P2 advertised as its adjacency SID to P5. So it also looks at that and goes, oh, okay, I've got to send the traffic directly to P5 over this link. So it pops that label as well. So now the packet is sent with just one single label, which is 800. So P5 looks at that and he goes, okay, I'm going to swap 800 for 800 because 800 is P2's SID, goes to P6. P6 does a penultimate hop pop, right? So it pops the 800 and sends the packet directly to P2 and we are happy it's made its way. So I hope that made sense, but let's just recap, the key learnings out of this. If I look at the right example, what have you achieved, right? We had a requirement, a business requirement, or a technology requirement, to avoid the link between P2 and P3. As soon as you do that, it's no longer an IGP decision. I mean, you could have done it through IGP. You could have set the metric to be very high, but then you might also have a requirement to use that link for certain traffic, maybe your best effort traffic. So that doesn't cater for all the scenarios. So you had this business requirement for traffic to flow this way. Now, you do not want the network, as in the P routers, to be able to have to make that decision on how to route packets for a certain flow. So what you do is you encode that information in the packet itself. So now the instructions are in the packet, and all your network has to do is adhere to the instructions as it looks, as it goes through the network. It looks at the labels and it acts on it. And by virtue of that, we're able to do traffic engineering between P1 and P2, avoid the P2 to P3 link, send the traffic directly over the P2 to P5 link, and there is no extra state in the network. So that's segment routing in a nutshell. And now I'll go back to a bit of theory, but I'll go through it pretty quickly because I think that's something you can go back and read in your time. The key thing is that you understand the concept of segment routing. So I've got about 6 or 7 minutes until the break, so I'll go through this theory really, really quickly. If you do have any questions, I don't see any yet. So I hope that's all made sense. But in any case, I'll open it up for questions at the beginning of the next hour. Okay, so let's keep going. Operations on segments. So segments have a similar set of operations as we have with MPLS. So with MPLS, you push when you add a new label, you pop when you remove a label, and you swap when you replace a label with another label. In segment routing, we call it push, just like MPLS. We call it next for pop instead of pop, and we use continue for swap. And the reason for that is because it's not just MPLS. We have a IPv6 data plane as well. So this terminology actually applies to both MPLS and IPv6. We've already spoken about segment routing with the MPLS data plane, where we encode MPLS label, or we encode the segment route ID within the MPLS label. And we use these operations, though I've already spoken about this. I'll quickly go through this. Now, a few concepts. I spoke about having this global allocation of labels. Now, how do you do this, right? How do you get these routers to agree on what is a global range? The way it's done in segment routing is by using this concept of a segment routing global block. So this is a chunk of labels that we carve out of the complete label space of the router. So in this case here, we've said labels 200,000 to 299,999 are reserved for global segment IDs. When building segment routing networks or segment routed networks, it's actually useful and recommended that all routers share the same segment routing global block. Because if they don't, then it's not that things won't work, it just gets a little bit more complicated. But when you have a multi-vendor implementation, it may be necessary. What is supported by one vendor's implementation may not be supported by another's. So you may have a scenario where you do have to use different SRGBs. So let's quickly go back to segments. you know, I kind of simplified this, oversimplified this, and said there are two types of segments: your nodes and your links. I'd like to delve a little bit deeper into this, because you will come across this as you enhance your learning of segment routing. So you've got segments that are called IGP segments, and this is a term for segments that are advertised by the IGP itself. Now, within an IGP segment, you could have what we call prefix segments. So this is a segment that is associated with an IP prefix. There are a few types of these. So there could be a node segment that identifies a node, and then you could have things like an anycast segment that's identifying a group of nodes that are part of an anycast set. Now, you could also have these adjacency segments that I spoke about, right, which is identifying links. We've also got segments for BGP, and with BGP, we've got things like prefix segments, once again, just like you have for the IGP, where there is a segment ID associated with a prefix that is advertised by BGP. And then you've got this concept of egress peer engineering segments. Now, if you have time today, we may go through some of these examples of how, egress peer engineering segments are utilized in the network. And you've got different types of these EPE segments that we call associated with specific BGP, eBGP peers, with adjacencies to eBGP peers, and to groups of eBGP peers. And so, you know, this is just a quick summary. There's a bit of detail here. I'm not going to go through it now. You will have all the slides, so you can go through this in a bit more detail. I've got quite a bit of detail on all the different types of segments, your anycast segments, and so on. So I believe I've got a, I may have a question here, so give me a second. Let me just have a look at that now before we break. Okay, so question there is that why is a SID swap still there in SR when there's no requirement in general? And I think that's an excellent question, Subin. So the reason we have a SID swap is so that we can reuse the MPLS infrastructure. Now think about an MPLS data plane implementation. There is no MPLS data plane implementation where a transit node just takes a packet, an MPLS packet, and sends it out without change, right? We do not have that. So in order to in order to function as a transit LSR, the implementation always requires a swap. So in order to reuse the MPLS architecture, we had to have this swap, even if it's just replacing a label with another label with the same ID. So I hope that makes sense. But if not, we can have a chat offline. Okay, so I think I might stop at this point. Dibya, I believe we have a 15-minute break, don't we?
Yes, Paris, we have 15 minutes break.
Okay, thanks, guys. So yeah, we'll resume in 15 minutes time. If you do have any other questions that you can think of, please go ahead and use the Q&A window so that everyone else can get the benefit of that as well. Yeah, thanks for your time. Welcome back. Let's keep going here. So we had a question at the end of the last hour about why we need swap, and it's quite fortuitous because my next slide kind of explains how that actually works. So this is an example here, which is similar to what we've discussed already, but with a little bit more detail. So as we saw, all routers advertise what we call the node SID, right? And this is done through the IGP, and it's installed in the MPLS data plane. So in this case here, we see that in this network, which 2P routers, 3 transit routers, we've got P2 advertising node SID 800 for itself. And it's done through the IGP. What happens is that P3 gets it, and P3 makes an entry in its label forwarding information base, right? Which is the call it, it's like a FIB, right? But for MPLS. And the entry is, if it gets an incoming label of 800, it's going to send it out to P2, and it'll pop the label, because remember we're doing PHP in this case. P2, on the other hand, puts an entry in that says in label 800, out label 800. And P1 does this similar thing. Now, PE1 has to put an entry that associates P2 with that SID. So it says, if my destination is P2, I'll put a label of 800 on it. And my interface is the interface to P1. So when, sorry, let me just do this again. Okay. So now when a packet comes in from P1 that's destined for P2, it pushes a label of 800, right? It goes to P1. P1 swaps the 800 for 800, as we had earlier. P2 does the same. P3 does the same. Oh, sorry, P3 pops the label, sends it on to P2. So you see that the swapping of label for label is really as a consequence of the entry that we make in the label forwarding information base that associates that in label with the same out label. And we do that, as I explained earlier, because that's how MPLS works. It's got to do a swap. You can't just send a packet as is. Just like an IP router cannot do that, right? I mean, we always decrement the TTL and all that kind of stuff. So it's, in order to retain the same forwarding mechanism, we need to be able to swap the label. But we do not want to change the label. So we keep the label to be the same value. So the key thing, as I mentioned, is that what's being stored in the routers, the P1, P2, P3, in terms of state, is just the information in order to get to other routers in the network. So in this case here, it's got information about P2 and how to reach PE2, but it's got no tunnel specific information in it because it doesn't require it. And that's the reason we're doing segment routing in this context here. So I hope that sort of clarifies how that actually works. Now, it kind of comes to the conclusion of this first section on introducing the technology of segment routing. And this table should be familiar. We went through the Ldp and Rsvpe comparison earlier. Now to add SR to the mix, it is actually a multi-point to point construct by virtue of the fact that we are not building stitched up tunnels in the network. So many nodes can send traffic to the same destination node using the same label. Now the operation is actually simple, right, in this context, because all you're doing is turning on your segment routing extensions on your IGP. In terms of dependencies, it does rely on the IGP, of course, right? Because the IGP is needed for the shortest path forwarding plus the advertisement of the segment information. Our label allocation in this case is global, as I mentioned, and this is key to it. We can do traffic engineering. The number of labels is also limited, right? We're doing one label per node or local interface. Now, there are extensions to segment routing using something called Flex Algo, where you can have multiple labels per node for different algorithms. We don't have time to go into that, but it could be more than that, but it's still not on a per tunnel basis. And it gives you that 100% coverage when it comes to fast reroute, and natively supports IPv6, as I said earlier. So no, it's if you look at segment routing, it's like the best of both worlds between LDP and Rsvpe. Right. So in the remainder of this presentation, I'll spend some time going through the use cases, and judging from how successful I've been so far, I don't think I'll be able to cover all of them. So what I'll do is I'll cover a few of the use cases, and then I'll jump to the deployment scenarios section and cover that quickly as well, leaving a few minutes for questions at the end. So use cases and applicability. A number of different use cases, as I mentioned. Now, the most basic use case is just shortest path forwarding, and this is one that doesn't require anything really complex. As I said, if you take this example here, if all of these nodes are enabled for segment routing, they all advertise their SIDs into the IGP. And once they've done that, for any node to reach any other node in the network, all it needs to do is build a packet or get a packet from somewhere, like from one of its incoming interfaces, put a label on it that corresponds to the destination node, and it'll get there through the shortest path. So in this case here, if you look at this network, for P2, nodes P1 and P2 will put in a label forwarding entry that says, if I get something with a label of 800, swap it for 800, similar to the last example. And P3, on the other hand, will take an incoming label of 800 and pop it, because it's the penultimate hop. So very simple kind of scenario. Why would you do this? Well, you do this because you don't need to run LDP now. All of it's done through the IGP. And for a lot of basic services out there, that could be all you need. So just going through this very quickly again. Your packets is your P1 slaps a label of 800 on it. It's been the top label is 800, so comes to P1, it swaps 800 for 800, sends it to P2, swaps 800 for 800, goes to P3, and here it's gonna do a pop. So it pops the 800 and sends the packet to PE2. All right. Just saw a question come in, or did I? Okay. Question from someone about, can we use legacy Ldp, Rsvpe, and SR simultaneously? What could be the best transitioning mechanism? We'll come to that. That's the last section. So good question. I'm glad I've got an answer for that as well. So if you give me about 20-25 minutes, we'll get to that. Okay, now consider this same network here that we have, right? Where all of the IGP link costs are identical. Now, clearly, in such a network, you've got two equal cost paths between PE1 and PE2. And assuming that ECMP is enabled on PE1, then we should be able to use both paths, right? You'll be able to share traffic across it. Now, one of the benefits of segment routing, especially when coupled with an SDN controller, is that you could use the two paths in a selective fashion. Now, remember, one of the things that I've been going on about is the ability to do routing on a per flow basis, which means different flows. And by flow, I mean, a flow could be different things, right? A unique source and destination IP address combination could be a flow, or it could be a bit more granular, that you're going from it could be from one socket to another on a router. So it could be a bit more granular. It could be a 5-tuple based kind of flow. Doesn't really matter. It could be fairly arbitrary, but no matter how you define your flow, you may have a requirement to route flows differently. So in this case here, what you could do is you could program P1 that says, for flow M, whatever M is, doesn't really matter, route it over the top link or top set of links. For flow N, route it over the bottom set of links, right? And so you have that flexibility, even with shortest path routing, to be able to dictate which path is actually being taken. Okay, now we do source routing with a node SIDs, right? So I spoke about how we can do traffic engineering using either node SIDs or adjacency SIDs or both of them. So one way of doing this is, if you wanted to specify a path between, between P1 and P2, you could specify explicitly every single link that it's going to go through, right? So you could say it's got to go P1 to P1 to P4 to P5 to P2 to P3 to P6 and P2. You could do that. You can specify all of them to some extent. The challenge with that is that your label stack starts to grow. And that may be an issue because, depending on hardware, you may not be able to support such a large label stack. Because in typical MPLS implementations, we see 3, 4, 5 labels maybe. But it's just as soon as you start getting higher than that, then there could be hardware limitations that you have to contend with. So, excuse me. We once again have this requirement, and this is the example that I had earlier, where you want to avoid the link between P2 and P3. So one way of doing this is a label stack that looks like this. So it says, think of it once again as instructions. So the instructions here are, take me to node 300, shortest path to 300, which is this node. Once there, take me to node 600, which is P5. And then once you're there, send me to node 800, which is P2. So this will go through this way, right? So P1 sends it to P1. P1 does a swap of 300 for 300. Remember that 300 is a SID that was advertised by P2. So the entry in P1 will be swap 300 for 300. You would also have an entry for SID 400 and 500 and 600 and 700 and 800, all of them. But in this case, the one it's looking at is the one that is 300. So it does the swap, sends it to P2. Now P2 is node SID 300, so it pops it. It then looks at the top label, which is 600, which happens to be the SID for P5. So it sends it to P5. P5 looks at it and it pops because that belongs to itself. It's left with a packet with a single label of 800. And so it sends it on towards P2. Gets to P6. P6 will do a penultimate hop pop. And it's, and then it sends it out to PE2. Right? So that's one way of doing it. Now think about just a sort of mental exercise for you. If the label stack that we put on this was 600, 800, what would happen? I'll give you like 60 seconds or 30 seconds to think about this. Instead of doing 300, 600, and 800, it was just 600, 800. How would the packet go? And if someone wants to put it in the chat window, I think that'll be cool. Okay, no takers yet. It's in the Q&A window. Based on IGP reach 600. Exactly. So we've got a correct answer. So what would happen here is, if it's 600, 800, right? Remember what the node SID means. Take the shortest path to that node. The shortest path to P5 is this bottom path. So it would go this way, and then it would go to P2. But it would not go through P2. So it changes the path. So you got to be careful about how this is constructed. So thank you for that. Bit of audience participation is always good. Okay, the next use case that I want to touch on is what we call disjointness. It's a bit of a mouthful, but this is a scenario where you've got to build two services that are completely disjoint of each other. And what I mean by disjoint is that the path of one service has no common points no intersection with the path of the second service. Why is that important? It's important because you might be building a highly diverse service where you want the ability to have two paths that are completely disjoint. So there's no single point of failure that links both of them. So if one fails, you're guaranteed that the other one will be up. Now, one of the situations where we use this is in dual plane networks. Right? A lot of operators build dual plane cores, for example, where they have two separate core networks. And they, you want to keep the primary service on one core and a backup and the backup on the other core. So if for whatever catastrophic reason one core is gone, then at least you guaranteed that the backup path is on a different network altogether. So here's an example, right? And this is a bit yeah, there's a bit going on here. So let me try and explain very quickly. This is a dual plane network. So what you've got at the top here is the red plane. So this is a set of core routers, P1, 2, 5, and 6. And you've got a blue plane, a P3, 4, 7, and 8. And you've got a bunch of provider edge routers. And the way the provider edge routers are connected is they are connected to both planes, right? So P1 has links to P1 in the red plane, and P1 has a link to P3 in the blue plane, and so on and so forth for all of the other ones. Now, what we want is we want to build one service that is between P1 and P3, but uses the top plane, the red plane, right? So what we do here is, sorry, before I go into that, we also have another service that is built from P2 to P4. That needs to use the blue plane. And so you can see here that the path from P2 to P4 and the path from P1 to P3 is completely disjoint. We're going through, there are no common elements in the path. So how do we do this, right? So key to this is we set up this plane as an anycast set. And so instead of, well, not instead of, but in addition to having node SIDs for these nodes, we assign an anycast SID for this set. And in this case here, the SID is 902. And for the bottom plane, the blue plane, we have an anycast SID of 901. So now it becomes actually very simple to ensure that traffic from P1 is being sent over the red plane. We build this label stack, right? This label stack is 902 and 300. So 902 for the anycast SID and 300 for the destination. And that 902 ensures that this traffic will go through the anycast, the red plane, right? And for service 2, it's 901 and 400. So that ensures that the destination is 400, and it's going to go through the blue plane, which has a SID of 901. So this is a very simple way of providing disjointness through smart use of segment routing and an anycast SID. Okay, just quickly look at the questions again. Okay, it's all good. All right. Now, an interesting use case. This is where BGP segments come in, and I briefly alluded to that before before the break. Now, let's look at this network. Let me talk you through it, and then I'll go through what what we can do with this. So, assume that this is your AS 100, and in your AS you've got routers R2 and R1, you're peering with two other ASs. So there's AS200 and AS300. Now with AS200, you've got two peerings with R7 and R8. And with AS300, you've got a single peering, but it's a multi-hop eBGP session, right? So you've got two links between R1 and R9. Now, additionally, you've got a you call it an SDN controller of some sort or something that is running BGP LS. Now we haven't already touched on BGP LS in this tutorial, but in short, BGP LS is a term for BGP link state, and this is an extension to BGP that allows the gives us the ability to convert IGP state into BGP advertisements. So what that means is that by virtue of this link state capability in BGP, your controller can get an understanding of your IGP topology. So very powerful. So this is how your SDN controller builds its, gets visibility into the topology of the network through BGP-LS. Now we've also got BGP flow spec happening between the EP controller and R2. So this is just to set things up. I'll talk you through what that actually means. Now, egress peer engineering, as I said earlier, and I went through this really quickly. It allows you to have three different types of segments. Now, the first one is what I call a peer node SID. So for R1, it'll have a node SID for R7, for R8, and R9. This is how it refers to its BGP peers, right? It's a segment that identifies a BGP peer. Now you have the concept of peer adjacency SID as well. Now, for peers with whom we have just a single link, right? That's not very useful. But in a multi-hop BGP scenario, that is useful because it helps to distinguish between the two different links that we have. So there'll be a SID that identifies each of these links. And then you have a peer set SID. So a peer set SID is a SID that identifies a set of peers. So for example, you can have a SID that is for R7 and R8, which are the two pairs in AS200, right? So what we would have now is we'll have a node SID for R7, R8, and 9, the peer node SID. We'll have peer adjacency SID for these two links. And we'll have a peer set SID that goes across R7 and R8, right? So it's a collective SID for the two peers that we have in AS200. Okay, so here's what we want to do now. The router allocates these SIDs. Okay, what it then does is that it actually advertises the SIDs using BGP LS to the EPE controller. So there are some segment routing extensions for BGP LS that allow us to do that. And this controller then has the ability to configure other routers in the network. So how can we actually use this, right? So the question is, what can we do with this? So here's a set of examples that make this possible. Now, a common challenge we might have in a network is if, for example, AS100 is a transit, AS, it's got traffic coming in from R2 or into R2, and it could go either through AS200 or AS300, right? Following normal BGP, based path selection. Or you might want to have a bit more control over it, a bit more sort of granular control over picking your egress point. We know that's a challenging thing in BGP networks, right? How do you control that Now, the egress peer selection is an interesting challenge. So what you can do here now is, because this controller has visibility of the segments, and it's got awareness of what flows need to be, or it's got an understanding through configuration or otherwise of how to deal with flows, we can actually put some, advertise some flow entries to R2. So one example could be that 80% of the traffic that is entering R2 that is destined should be sent over to AS300. And the segment list you should use to do that is 100 and 1005. So let's think about this, right? 100 is the SID for R1. What is 1005? Now, I've got a table here that's got them. 1005 is the SID for R9, the node SID for R9. So remember I said that there is a node SID advertised for every peer. What does that mean? Because we haven't specified a particular link, it means that when a packet gets to R1 with a SID of 1005, it'll load share that traffic, load balance the traffic over the two links to R9, right? Because that's what that SID says. So that's one action. We could then say, send 20% of the traffic out to AS200 and put a segment list of 100, 1006. Now 1006 is saying load balance on any link to R7 or R8. So 1006 is actually a peer set SID, because it will round robin on a per flow basis between R7 and R8 and send traffic equally to it. So in a similar way, you could have a flow entry for any prefix with a certain amount of weighting that controls exactly which peer, which link it's using on its egress. So for example, in this case, you could send something to 1003, which is the upper link to R9, or 1004, which is the lower link to R9. So this gives you a bit more control over how traffic is leaving your network. So quite a powerful mechanism. Now this is really an advanced use case of segment routing, because it's bringing together things like the BGP EPE extensions, the concept of BGP LS with segment routing extensions, an SDN controller, the use of BGP flow spec, and so on. So, but this is the true power of SDN and segment routing being harnessed here. All right, I'll do a couple of more use cases, and then we'll move on to looking at some of the deployment scenarios. So this is a scenario where, once again, you've got a pretty simple network. Traffic being sent from provider edge P1 to P2. And what you've got is between P1 and P2, you have two links. One's a 10 gig link and the other is a 400 gig link. So let's just say, in the absence of any special configuration, what would happen? If we turned on segment routing, it'd be pretty simple, right? You'd have P2 advertising a node SID of 800. So P1, to send traffic to P2, would use a node SID of 800. It'd go to P1 and swap 800 for 800, and then it would send it out on the lower link. It would send it out on the lower link because it's doing shortest path forwarding. And that means that this 10 gig link will not be utilized at all, right? Assuming that there are, the metrics are based on capacity. So, this is not an ideal situation to have. So one of the things that we can do here is use the concept of the adjacency SID. So let's look at how this works. Now, on node P1, we will allocate SIDs for each of the adjacencies, as we do automatically anyways. So there'll be a SID for the 10 gig link, which is 1001. There'll be SID for the 400 gig link, sorry, for the 40 gig link, which is 1002. And then we'll configure a new adjacency SID for the set of links, for the 2 links. And that's going to be 1003. So these links will also be part of an adjacency set with a SID of 1003. Now, we also assign weights to them. So as you can see here, the 10 gig link has been assigned a weight of 1, and the 40 gig link has been assigned a weight of 4. So it's in proportion to their relative capacities. So what's going to happen now is when PE1 sends traffic to PE2, what it's going to do is it's a little bit more complex. So in the previous example, it would just put a SID of 800, a label stack of just 1. But in this example, what it's doing is it's putting a label of 200, which is the SID for P1, and then it's putting a label for the adjacency set SID, the 1003. Now, when it comes to when it comes to P1, it's going to pop 200, as you can see here. It's going to look at 1003. It'll look that up, and it'll see that for that 1003 represents an adjacency set. And so it'll load balance traffic in a 1-to-4 fashion between the 10 gig and the 40 gig link. And that way you ensure that you end up using both of the links. Hope that makes sense. Now, there is an optimization here, of course. There was really no need to put the 200 in there, if you think about it. Because P1 and P1 are directly connected, even if it did not have the 200, it'll have the same impact. It's just an optimization. But anyways, that's not super important. Okay, so now what I'm going to do is, okay, I'll just do this use case and move on to the deployment scenarios. Okay, so segment routing, we've seen some examples where we couple this with a controller, with BGPLS, with global visibility, and it becomes pretty powerful. But what if you wanted to just emulate what we have with Rsvpe? No global visibility, but at the same time, we still want to use CSPF, right? Constrained shortest path first. Can we do this? And the answer is absolutely yes. So just like we do a distributed CSPF calculation on routers today with Rsvpe, we can use the same information, right, that is advertised by the traffic engineering extensions for Rsvpe. So things like the bandwidth we have available on links, how much of it is used, how much available, things like admin groups, right, affinity, shared risk link groups, separate the TE metrics, and so on. So looking at this example here, one of these things is, let's just say we've designated the link between P1 and P2 to be part of a shared risk link group 1. Now that is advertised into the IGP, right, through the IGP extensions. So now what would happen is, let's just say that P1 wants to compute a path to P2, but it's got a requirement not to use this particular link, this shared risk link group. So what it would do is, just like in the case of Rsvpe, the CSPF calculation would actually remove this link from its tree, right? From its shortest path tree. So it prunes the link, and then it calculates the path. So in this case, the path will obviously be the longest possible path, which is traversing every single router. And in this case, P1 would then impose a segment list of 200, 500, 600, 300, 800. Now, once again, this is an uncompressed list, we can be smarter, right? If we did a similar thing with a list called with a list with just 3 entries, 500, 600, and 800, we would achieve the same thing, right? Because the shortest path from P1 to P3 is still this one here. Shortest path from P3 to, well, it has to go to P4. And then the shortest path from P4 to PE2 is still through P2. So we'll achieve the same thing. So there's a few other use cases I've got here, which we will not have time to go through today, but they're in the deck. So please have a read of them, and if you do have any questions, let me know. In the meantime, I will now jump to the next section. Okay. I trust you can all see that now. So the final section is how do you go about deploying this? And we had a question about this earlier in the session. Now, there are 2 broad categories, as I said earlier. One is greenfields. Now, we know that greenfields don't really exist. There are very few greenfields out there. But in the case of segment routing, it's been a bit different. And for a lot of large operators, the advent of 5G and the necessity to build a brand new 5G transport network has actually meant that they've built greenfields networks for 5G transport between the radio access network and the core, and so on. And so this is not a theoretical thing. It actually has been an option for a lot of operators. So greenfields, pretty straightforward. You would need obviously hardware and software that can support segment routing, obviously, and there's an opportunity to bypass LDP or Rsvpe altogether. Now, at the same time, there are still some caveats, right? No matter which implementation you go for, given that it's still, even though segment routing has been around for 7 or 8 years, it's still an active area of work within the Ietf. There are new drafts, there are lots of new drafts. There's a lot of work still happening with segment routing. So you need to ensure that the feature set that you're after is available in whatever implementation you choose to go with. But on the whole, greenfields, pretty simple. Now, brownfields networks, right? Or they are actually not that dissimilar to greenfields, or at least the considerations are not that dissimilar, because segment routing, if you recall, the beginning part of the presentation when I said that one of the objectives and requirements actually that segment routing had imposed on itself was that there should be an ability to gracefully introduce it into existing networks, right? So it should be incrementally deployable. And what that means is that with segment routing, you have the ability to introduce it into networks without disrupting existing services. So just like a lot of things that we run in IP networks, you can run segment routing in a ships in the night kind of manner with Ldp and Rsvpe. Now, that doesn't mean that you do not need to think about it, or it's completely transparent. That there are some considerations. Remember that you're doing things like carving out that block of labels for the sRGB. So you need to consider that. But having said that, once you've done all that, they can work together. There's nothing stopping all 3 from running in the same network at the same time. So the option, it gives you the option now that if you introduce segment routing in your network, you can build new services, some new services using segment routing, and leave the rest on your existing Ldp and Rsvpe framework, and then migrate over time. So look at some of these cases. Now, just back on this segment routing and Ldp in particular, right? So when you look at implementations, you'll see that any of the control planes that we have, ends up installing or advertising reachability information, forwarding information, and then installing it into the data plane, right? So IP routers, of course, we install IP routes into our Rsvpe and all that, and it's the same for MPLS. So it's pretty clear that when you're sharing this infrastructure, they must work together, right? So that the same label is not assigned by multiple clients of that router, right? Of that MPLS label table, which kind of happens pretty much automatically, but it's important because it needs to be there in order to function as ships in the night. So some of the scenarios, right? So there could be a scenario where you've got some routers, or all routers in the network are running both LDP and SR. So you could start off with an LDP network and then upgrade these routers with segment routing capability. So now you've got both. So then it becomes a local decision at the router on whether you use LDP or use segment routing. And there's many ways of influencing that, right? So your administrative distances, your preferences, whatever you call it, to dictate whether, given a choice between two tunnels to the same destination, one segment routed and one LDP, which one do you select, right? So that can be done, and it can be gracefully done as well. Now, the other scenario is where you have a network where segment routing is only available in some parts of the network. So you have a mixed scenario here. There are some routers that support LDP and SR, some that support SR, and some that only support LDP. So you need to cater for that kind of scenario as well. And this could arise in large networks, for example, where the feasibility of doing mass upgrades in order to enable SR may be limited. Right? You may have thousands of access nodes running LDP that need a new image or maybe even new hardware, which makes it prohibitive. But you still want to run SR. How do you do it? So we'll look at this case shortly. So ships in the night, right? Coexistence. So I'll go through this really quickly. Now, in this network here, what I've got is the nodes that are pure green are LDP only. The nodes that are blue, in which case none of them, are SR only. Now, I assume that there will not be any segment routing node anywhere that does not support LDP, right? You think LDP is a basic thing. But then you've also got these nodes that are a blend that support both LDP and SR. So in this network, P2, P1, P2, P3, PE4 support both LDP and SR, and P1 and P3 only supports LDP. So pretty clear. If you want to build a service between P1 and P3, it can only be LDP. And if you want to build a service between P2 and P4, it can be LDP or SR, right? We'll prefer SR in this case. So what you do is we just set it up, right? So that the tunnel PE1 does not have a choice. It needs to use LDP. So let's just say that it's got a service label of 910, which is the inner label, and puts a transport label of 423, which is P1's label for PE3. And then it goes through the usual LDP swaps. You can see the label is changing all the way up to PE3. On the other hand, with P2, we use an SR tunnel where the VPN label is 860, but the transport label for P4, which is the node SID, is 204. And in this case, you can see that the label stays the same as it goes through the network using segment routing. So this is all possible. There's nothing really special in your network for this to work, right? So ships in the night works really well. Okay, now I've kind of covered this. I'll jump. Now, how do you migrate from LDP to SR? So let's just say you do have this greenfields kind of scenario. In this network, it's all LDP only routers. And all of the services you have are being tunneled using LDP. So first stage, they're all running LDP. Everything's being tunneled through LDP. The second stage is where you upgrade your routers to segment routing. Now, when I say upgrade routers to segment routing, what do I mean? I mean potentially upgrading your operating system so that it's got segment routing capability, and then configuring it so that the base segment routing infrastructure is configured. So things like your segment routing global block, right? So in this case, we're setting a global block from 100 to 300. Second thing is assigning node sits. So all of them have node sits assigned to them as well. But nothing changes. You still continue to use LDP. You set up the segment routing infrastructure, but LDP is still preferred for your services, right? Now, the third thing you do is you start off with, let's just say, one PE or a pair of PEs, right? And you go, PE1, I will configure it so that instead of LDP, it now prefers segment routing. So now, services from PE1 to any other PE that supports segment routing will use segment routing. Everything else is still transported over LDP LSPs. So, okay, you got a bit of a field trial going on with one PE that's using segment routing. Then, over time, you upgrade all of the routers to prefer SR over LDP encapsulation. So you get to a phase now where everything is being transported over segment routing. But you leave LDP running. It's not doing much, but it's there in case something stuffs up, right? So you got to fall back. And then after a period of time, you deconfigure LDP. So all the running is segment routing. So this is one way of doing it, right? To migrate fully from segment routing to LDP. Now, the last scenario that I wanted to talk about, and I'll go through this a little bit quickly because it's a little bit involved, is where you have the scenario where you've got some routers that are LDP only, and other routers that support LDP and SR, and then again you've got some routers that are only SR because you've configured it that way. So let's have a look at this, right? It's a very complex network, and I hope you never come across this in reality, but it could happen, right? We could, because of hardware dependencies, you may have a desire to move to segment routing, but are not able to for certain routers. So you may be stuck with older software, older hardware that does not support segment routing, but you do want to go to SR. So what do? You could do this. So in this network here, you've got routers A and B that are only LDP, right? Router 1 supports both LDP and SR. Router 3 supports LDP and SR. Routers 2, 4, and 5 support only segment routing. Okay. Now the trick is, how do you send traffic from A to B? Now, remember that we're running LDP in this part of the network between router A and R1, and we're running LDP between router 3 and router B. So if router A has to send traffic to router B via LDP, what does it do? It does not have a label for B. It does not have an LDP label for router B. So what needs to happen here is that router 1 has to advertise an LDP label for router B, right? So it's at the boundary of the LDP and the segment routing domain. So it advertises a label for router B. And then it creates a mapping to stitch that LDP label to the segment routed label for router B. Now here we run into the same problem. We do not have a segment routing label for router B because B is not running LDP. So this is where we have the concept of a mapping server. So a mapping server is one that assigns SIDs for nodes that are not SR capable. So node A and node B do not have segment routing enabled, but you kind of need that in order to go through a portion of the network that is segment routed. So it kind of it's like a surrogate. It advertises node segments for these two nodes. So now going back to my previous example, right? What would happen is that packet comes in from router A, and it's being sent to router B using the LDP label for router B that was advertised by R1. It comes to R1, R1 swaps that LDP label for node SID 202. Why 202? Because that's what it knows about router B, that router B has a segment routing SID of 202. It goes to router 3. Now, router 3 knows that this guy doesn't do segment routing. It just does LDP. So that has to re-swap it for the LDP label for router B. Now, I've probably lost most of you here by now. Unfortunately, we don't have a lot of time to go through this in more detail, but you'll see that the whole exercise becomes a bit challenging, right? So let me just cut through this and explain what are the key things that we need to think about in this scenario. Okay, so we've got LDP only nodes, right? Now, you see that the LDP network is disjoint, right? It's discontiguous. You've got a portion here and a portion here, and a segment routing island in the middle. So we've got to somehow join them up together. And the way we do it is within the segment routing network, we advertise node SIDs for the LDP nodes. And then at the edge between the SR and the LDP domain, we stitch between LDP and segment routing so that we are able to build this end-to-end connectivity between the LDP nodes through a segment routing only network. So I hope that doesn't put anyone off segment routing, but this is an unusual case, but it's possible. Okay, so I think that pretty much brings us to the end of the presentation. Okay, so let me try and conclude what we've gone through today. I've taken you through some of the basic motivations for segment routing. We went through some early examples of how segment routing works, some of the terminology associated with it, and then I went through some use cases for segment routing. We looked at both shortest path first, traffic engineering use cases. We looked at some more advanced use cases around BGP, especially with regards to egress, PA engineering. And then we looked at some of the ways of introducing segment routing into operational networks. So if I were to summarize this in a nutshell, segment routing, what does it do? It helps us to reduce control plane protocols, right? So we are able to get rid of a few protocols like Ldp, Rsvpe by making better use of the IGP. It's definitely there to improve scale, right? For a network that needs to be flow, to do flow-based traffic engineering in a network, it needs to scale. It helps us with IPv6 migration as well. There's inherent ability to support IPv6, and it goes hand in hand with SDN. Right? It allows us to really use the power of SDN, because SDN can and SDN controllers can give us this more optimal path placement based on things that go way beyond just metrics, like real-time utilization, latency, availability, and so on. So it allows that information to be actually used in the network by virtue of the fact that you can program the path into the header itself. And it covers, it gives you full protection coverage, traffic engineering, use cases like disjointness, and and it's also very useful for things like service chaining when you consider the introduction of virtualized services into the path of a traffic flow. So I might wrap it up here. Let me just have a look and see if there's any questions. Yeah, I don't see any questions here. Okay, in that case, I'd like to thank you for sitting through this this presentation. I hope that was useful. If you do have any questions, please reach out to me. I'm more than happy to answer it. So thank you very much again. Over to you, Divya.
Thank you, Paris. Thank you very much for that wonderful presentation. It was a great presentation, actually. I hope all the participants got a lot of things on segment routing. I think that's it for the day. And since this is our last session, I'd like to thank everyone for joining us today. So tomorrow we are also having another sessions. So we'll be continuing tutorials on securing the internet routing, RPKI and ROV implementations. And the later half of the day, we'll have 2 presentations, tutorial sessions from Imtihaz on system logs with Elastic Stack. And then the next one would be threat hunting with network traffic analysis. So I thank you all for joining today and hope to see you tomorrow. Thank you very much.